Good afternoon, everyone. And I'm very happy and I feel very proud to introduce my friend, brother, my very close friend, Mahalingam. He's a um, associate professor in Coimbatore College University, CA. And I'm very happy actually. Uh, Good afternoon, everyone. Dr. Sendil Kumar, is a wonderful scientist. He achieved a lot. Very briefly, I'll tell you some few things. He has done his MSc and a Ph.D. from Madras University, and also he did a B.Ed also. Okay. And he moved to, he did two postdocs, one from Taipei, Taiwan, National Taiwan University of Science, and another from United Kingdom. From first one is 2005 to 8, and then next one immediately 2008 to 2010. Then he joined in CLRI, Sikri Karakudi. He has published, more than 80 papers in peer-reviewed journals and two book chapters, including and three international patents also with his hand, and he has completed two major projects. And his interest is various, lot nanomaterials for electrochemical engineering, energy conversion and storage, electrocatalysts for CO2 reduction, oxygen reduction, reaction, electrocatalysis for oxygen evaluation, hydrogen evaluation, PMPM, alkaline electrodes for dye-sensitized solar cells, and microbial fuel cells, chemically modified electrodes for sensor applications include. So with these things, I invite Dr. Sendil Kumar for to deliver his talk. And the talk will be 40 minutes, 35 minutes talk, and 5 minutes discussion. Okay, thank you. Please.
Thank you, Dr. Sivakumar sir, for your nice introduction, nice and sweet. And then I welcome you all for the evening session. I hope you had a very good lunch, and I'm not going to disturb you in your sleep. So we will see something little bit no crossing with this water splitting and another solar area. So so my title is designing nanometer-based electrochemicals for green hydrogen production. Actually, you know that now all throughout the world, people are looking for the technology or science behind the green hydrogen production. Especially our country is now more focused on to creating hydrogen hub throughout this country to supply the next generation vehicles, especially fuel cell vehicles. So I would like to introduce my institute. Many people may not be knowing. So this is very close to your Madurai. So 2 hours by road, and then we are in the south part of the map. And then electrochemical science and technology, which is one of the main area of our institute. Uh, in CSIR, we have 5 different categories of institutions throughout the India, which is totally 37 laboratories are operating. So first is biological sciences, second one is chemical sciences, and third one is engineering sciences, and fourth one is information sciences, and fifth one is physical sciences. We comes under the category of the chemical sciences. And then our unit, we have one in Karaikudi, which is the main mother institute, and then one in Chennai, which is a business development institute, where we will be showcasing our fuel cells and batteries there for abroad people. And then another one is in Mandapam, where we are doing some sea level corrosion, where the pipeline corrosion is majorly discussed there. So in Sikri, we deal with more than fundamentals, corrosion, batteries, fuel cells, smart sensor, process engineering, metal finishing, metal science, electroorganics, and solar cells. So we all work in one single laboratory under one roof, but all electrochemical science and technology will be developed here. So one of the very finest and then largest laboratory in Southeast Asia for solely dedicated for electrochemical science and technology. And then I would request you to visit during our September 26th open day, because the only one day they will open for everyone. You can visit there, and then you can see the other going on, whatever the things are going inside. So we will move on. So we know almost one day you finished, and then all the people are now insisted that about the global warming and then energy crisis. Both are no separate problems, but are coming from the same issue. Because when you use fossil fuels, you are polluting the world because CO2 is there and sulfur, NO2, SO2 are there. So it affects our environment by acid rain or other things. So and then climate change we need to avoid. So that we need to avoid any kind of fossil fuels. So we will go for a technology which can use renewable, completely renewable, especially in electrochemical science and technology, where we can use wind energy and solar energy. But one thing is that there are three important reactions which is electrochemistry. They are used in all energy conversion storage devices. We can say oxygen reduction, oxygen evolution, and hydrogen evolution. So hydrogen evolution and oxygen evolution are gas evolution reactions because that we will produce a gas by supplying electrons. Oxygen reduction is nothing but we will supply oxygen gas and we will supply electron, we will convert them into current. So that is only used in fuel cell, oxygen reduction, but others are evolution reactions which are used in water splitting. So whatever you are seeing, photochemical water splitting or electrochemical water splitting, without this fundamental, you cannot understand the process very quickly. And then, so we need to understand the process so that we can solve the issue by understanding them and then by designing a new material or new catalyst or new process. Okay, so we'll go one by one. So why we are already talking about the hydrogen economy? Because it's as far as it says, the hydrogen gas is very the lightest, and then it has the highest mass specific content of fuels, and then it is ecologically neutral because if it spill it in on any space, it won't harm you. It is not neither acidic nor alkaline. So it is an ideal candidate for the fuel cell, which produces a very little emission. Only water is an emission molecule, so it won't emit any sulfur dioxide or NO2. So fuel cell only emit water. So hydrogen is safer than commonly used natural gas because if natural gas explodes, it diffuses. But if hydrogen explodes, it goes vertically. So you can avoid many dangerous accidents during this. Okay. The major outcome of the combustion of hydrogen in fuel cells are only water molecules, so the ecologically neutral molecules. So, but the problem is, many industries are producing, many countries are producing hydrogen gas, but the source of the hydrogen is very important because now we are little bit awakened that we cannot dump more and more fly ash or any carbon material on planet by producing hydrogen. So, what are the type of hydrogen production? Because we can use the natural gas or biogas. We can produce the hydrogen, but again you will end up with the carbon. Other one is coal gasification. We will end up with the fly ash, and then if you go for wood pyrolysis, again we will end up with the biomass produced gas or produce carbon. And then if you use oil from any natural sources, you can produce hydrogen. But again you will dump more and more carbon on Earth's crust, and then again alcohol-based alcohol can be used for hydrogen generation, but it is also not ecologically neutral. So we don't want to use the existing industrial process. So that's the problem now. Why we are talking very late? Because all the processes are one way or the other, environment pollution or dumping carbon or SO2, whatever the components are there. So we don't want to use this existing method. So we want to go away. But this is almost 20-year-old technology. The paper is now already published somewhere. But at the time, the process what listed here, everybody thought it may be too costly. But now, because 20 years that the journey has been done, very twists and turns, and then now we can able to solve the issues by one, because the solar energy now we can able to trap and then tap the material energy into conversion into electricity with a low cost, because it was not there 20 years ago. So now the solar energy becomes affordable cost, right? Because the production of solar panels and many things are available. So now we can produce the solar energy because we have sunny climate almost 300 days in the year, right? So we abundant sun energy we have. So we can produce solar energy by electricity. So the electricity can be used to electrolyze the water molecule. Then we can produce the hydrogen gas. So this may be a sustainable route, because we have both water and solar is available every day, and we have enough plenty. So this path may be the sustainable path. So if you use this methodology, we will not pollute the environment. We will not cause any SO2 or NO2 or any carbon emission, so that it will be a green So we can able to sustainably produce the hydrogen gas from the natural available sources. So this may be the one of the best route people are telling, right? So next we go for nowadays, as I mentioned, but nowadays we are having $3 to $5 per kilowatt hour. It's international standard because we have in our country we have around 10 to 12 rupees of unit cost for solar energy. So it's affordable cost only for us. But still we are playing because maybe you may be aware that India is more producing more and more large scale solar plant. By keeping this in mind, because we can able to trap more and more solar energy so that all coastal line areas can be used for the water electrolysis, so that direct seawater electrolysis can be possible in coming days. So our production of electricity from solar will be still cheaper in coming days, so that this electricity can be used for the electrolysis of water. So this will be a green hydrogen mission, because we want to use green hydrogen for the other fuel cell based vehicles. So this is the entire scenario. So if you go for the concept behind this, we can take water and you take the solar energy or wind energy available in our case, and then you use the energy to split the water, produce your hydrogen gas. You feed the hydrogen gas to your fuel cell, and then you run the vehicle. Extra energy can be tapped into your grid so that you can use it common other purposes. And then finally your the fuel cell will be producing only water molecule as an emission product. So you will end up with the water molecule. So you started with your water as a starting material, and you are end up with the water molecule. So the cycle will be very green, and then close the cycle, and then this is the green hydrogen mission. So that only thing is, so we should focus on the production part and then as well as the storage part. So this is the concept where we can use solar and wind to electrolysis your water, and then use large scale storage, or you can use your pipeline storage we have, because we are thinking about the how to connect all the cities or all the existing pipelines. So by putting other extra lines, so that we can transport the hydrogen fuels without too much cost wastage, so that your fuel cell stations will be supplied by the green hydrogen mission, so that all the fuel cell vehicles can be run by this fuel cell. So fuel cell, I know I'm talking about fuel cell now. It's a very simple device where it has anode and cathode separated by a proton exchange membrane. It will conduct only proton. It will conduct proton by H plus as a carrier. So there in anode we will use the platinum as a catalyst, where the hydrogen gas is supplied. The hydrogen will be oxidized, and then it will produce as a H plus, and then the H plus crosses to the membrane and goes to the cathode side, and then electrons are passing through the outer circuit where you are using the electrons as your useful energy, and then the cathode oxygen will be supplied, and then it combines with the proton and the electron and forms a water molecule. So in anode we are oxidizing the hydrogen to photon and electrons. In cathode we are consuming the proton and electron along with the oxygen gas. We are producing the hydrogen water molecule. So this is a device which will use hydrogen and oxygen as a fuel, and then it will produce a water as a byproduct along with your energy. So we know that all the many big industries are already ready with their fuel cell gadget vehicles, like batteries, fuel cell based laptops, or power stations for any big buildings. Test systems are already ready. So only thing now, many companies even in India are ready with their automobiles along with the fuel cell based packages. Even people with people are working on fuel cell hybrid with battery also, lithium battery also. So many companies are already have their own technology. So even buses, even in Europe, some companies are fueling their trains with the hydrogen gas. So they are ready with this. But only thing is, are we ready to use green hydrogen in all fuel cells? Because still the hydrogen is coming from industry, which is having more of CO poisoning because it is from decarbonization. So the green hydrogen mission is still not yet taken to the 100% initial state. So there are a lot of scope for researchers, especially for engineers designing new materials or processes which can uplift the production of green hydrogen gas, as well as the vehicles and other applications. So there are many fundamental questions still need to be answered. So electrochemical water splitting, for your PG classes, you have now learned that if you put two electrodes, platinum electrodes in acidified water, if you apply a 1.5 voltage, the cathode will evolve hydrogen gas, and then the anode will evolve your oxygen gas, right? So this is a normal water splitting, but in all the cases we use platinum as a electrode, because the platinum is a well-known electrocatalyst for the water splitting, acidified water splitting, for because it has more active centers and more active edge sites for splitting the water molecule, right? So there are many companies producing a on-site hydrogen generator, which is based on pure platinum, especially the hydrogenics system, but they are very costly because these are not affordable for fuel cell vehicle based applications. So these are all only applicable for very remote sensing applications. And then many people felt that the more than 40% cost of this system comes from the catalyst what we are employing, because we need to have more than 0.2 to 0.4 milligram per centimeter squared loading of cathode and anode. So the catalyst cost of the platinum is too much. So it's also fluctuating every day. So we cannot afford this much cost in a fuel cell based vehicles. So so people now actively looking for a replacement to do the job of platinum, but it's not easy because it's a God-given gift. Platinum will take care of both HER and OER, but if you want to go for a non-platinum based material, so it's very very difficult, because we need to look many things. Cost is one thing. Other thing is performance, which should be very active. It should be low over potential material, and then property wise, there are many things that need to be tuned, because surface morphology or porosity or phases of the crystal phases and many things. So in chemistry wise, there are a lot of scope for researchers where you can put your knowledge and then efforts to produce a non-noble metal based material. In the case of HER, hydrogen evolution reaction, to replace completely the platinum from the electrolyzer application. So because the cost of the platinum is every day changing, $32 per gram, maybe tomorrow may be different. So we are thinking to how to replace the material, platinum, by using a non-noble metal material, so that we can go for a low cost green hydrogen production. So in the first phase, I will show you a non-metal MOS based electrocatalysis of hydrogen evolution. So we know that in industry it's called as a molybdenum sulfide. It's a very well-known lubricant which is used in heavy machineries. Now it's a layered chalcogenide material. So MOS2 belongs to a layered transition metal chalcogenide. So MOS in both amorphous and crystalline forms are active, because almost 10 years people are working on it. Both forms are active, but the stability is different, because amorphous will be highly active sometimes rather than your crystalline form, but stability may be different. And the MOS2 could be prepared by different morphologies, because if the morphology difference, the surface area will be different. And then synthesis of novel architectures, very important thing is in any scale or any industry or any laboratory, a material should be prepared in highly purified form without any other impurities, so that we can use this for the industrial scale applications. So this is the structure of the MOS2, where the MO is sandwiched between two sulfur atoms. It's a layered material. We can able to take a single layer by layer, so that you can prepare the MOS2 even though it's layer form, but we can prepare in a powder form and in different morphologies. So I think I want to emphasize that here, because there is two forms of MOS2 normally. The 2H is the stable form, which is available at crust, but it's not active for HER. But the 1T is a metal stable form. It should be prepared in the laboratory, but it's highly unstable. So the stable form may not be that much active, but unstable form will be active, but we cannot able to hold the activity for a longer time. That's a problem in the MOS2. Because the stable form will be active because of due to the only active centers available on the surfaces, because the entire geometric area, the entire will not be useful for the hydrogen generation. Only a fraction of the geometric area will be used for the HER, so that the surface area versus electrochemical surface area will be totally different, so that the activity will be different. So in this case, we prepared MOS in 3 different morphologies, because we want to alter the morphology of the material, so that we can able to change the surface area or porosity. In this case of we use the sodium albite and then the thiostamide as a material, and then we can use the hydrothermal bomb. It is no, the depends on the conditions. 200 degree 36 hours means you will get a sheet formation, and then 240 degree for 24 hours means you will get a sphere formation, and 240 degree for 36 hours you will get a flake formation. Because it is confirmed from your XRD analysis. You can see that 01, 02 and 03, they have different alignment, but all of them almost belongs to same crystallography formation, but their forms, different phases are there. And then you can see the FESM analysis where the sheet and then flakes and then sphere formed in a quite different manner. And then if you go for bead analysis, the nanosheets doesn't have any surface area, but nanosphere forms 36 meters square per gram surface area, and nanoflakes forms 28.5 meters square per gram. So you have a difference in surface area if you change the morphology because of the morphological factors. And then if you go for TM analysis, you can see that the space, the shape of the materials are totally different, especially the nanospheres have some of the defect sites in the outer sphere of the surface. They have more active sites on the edges, and then you can see that then MO and then S are both distributed uniformly throughout the sphere morphology. That means the entire part, the middle part is completely hollow. So it's almost a hollow sphere-like morphology. So our methodology proves that even though it's a layered material, we can able to alter the morphology so that we can able to tune the bead surface area, because the bead surface area directly affects our electrochemical surface area. So if you go for electrochemical HCR analysis, we want to compare it with our pure platinum electrode with it starts around 0 volt. But when you go for a morphological change, especially for the S02 gives onset potential of around 150 millivolts. So other two, S01 and S02, nanoflakes and the nanospecies are not that much active for HCR. You can see that. So it reflects in the Tefl plot, where the platinum gives a very good Tefl plot around 35 millivolts per decade, but S02 gives around 40 or 40 to 50. But other S01 and S03 are not that much good. So what it says that the surface area directly improves the activity. Not only the surface area, but we go for the X-ray absorption studies where we can able to look in more detail about the MO bond S length. So in the case of S02, the sphere morphology, we have a distinctive structure of the MOS. The bond length is different than the nanosheet and nanoflakes. So that gives a more active edge sites, where one of our friend helped us to calculate the hydrogen proton adsorption and hydrogen desorption energy on S02 based structures, and then they found that the active centers are especially the S02 gives a very low adsorption for proton, similarly very low energy for the removal of the hydrogen gas which is formed on the surface. So that means it offers some more active centers to absorb easily the proton, as well as offers a very easy deposition of the hydrogen gas which is formed on the surface. So that means it acts more, it produces more hydrogen gas with a fraction of time. So that means that's called the TOF, turnover frequency number. We will be seeing later. So after that, we went for the single cell electrolyte studies, because anything you produce in a laboratory, it should obey in your system studies. Okay. So where we hand over the material to our nearby laboratory, where they use the single cell studies, where they employed the NAFN 117 in a 4 centimeter squared area. It's a little bit large scale. And the anode is composed of 2 milligrams centimeter square for iridium coated membrane. So anode is always a very active material for oxygen evolution. And cathode is our MOS to 2 milligrams centimeter squared, which is directly coated on membrane. And then conditions are we put a 2 volt, that means you polarize the 2 volt at 25 degree, and then you allow the continuous water flow, because as I said earlier, it's a complete system. You allow the water inside, you have the NAFN membrane, it's acidified membrane, so that you can apply the potential, and then you can get the hydrogen gas in the cathode and oxygen gas in the anode. So this is IV curve, where we polarization start from the 1.2, there is no hydrogen evolution. But if you go for beyond 1.4 volt, the hydrogen evolution starts, the current appears, and then it goes around up to 2 volt, where we got around 60 millivolts milliampere current density, because we want to see how the polarization occurs initially. And then what we did, actually we did at 2 volt at a constant current single cell potential operations, where we produce up to 65 milliampere per centimeter squared current density. A non-noble metal based material producing 65 milliampere is good for me. But when you compare with the platinum, it produces 1 ampere, almost 15 times higher current density. But the platinum is totally different, because platinum is a noble metal, its cost is too much. But when you go for MOS2, it's a non-noble metal material. We can able to prepare in large scale in our laboratory. But in the first step, it produces 65 milliampere per centimeter square. That's enough for me. So that it is what we need to think, how to improve further activity, the same material, but how to improve further. So we need to go for a improvement in conductivity, because the material is semiconductor material. So we want to deposit over a carbon nanotube. Among carbon nanotube, multi-wall carbon nanotube is a little bit low cost when compared to single wall. It has a large surface area, we know that, semi-metallic nature, so high mechanical stability and high electrical conductivity, and then it's a chemically inert, so that we can able to use in any conditions. So that we want to deposit the MOS2 over the multi-wall carbon nanotube. So we made it 15% loading we took. So we took 15% loading of MOS2 by synthesis itself, where we put together CNT, multi-wall CNT, and we decorated the material over the top, and then we grown it. So we have characterized them, both XRD and then FSM and HRTM. So the material grown over CNT is stable, and it has like flower shape. And then now we went to electrochemical part, where we can compare all the other previous material along with the MOS2 over CNT. We can see that the movement of the onset potential is very close to platinum nowadays. So when S02, the MOCNT is little bit more active than the S02. And then we can see that in the TEFL plot, where platinum and MOS2 decorated over CNT almost similar in the region. And then we calculate the exchange current density, it's equilibrium current density. For platinum, it's a 5.62 10 power minus 5 amperes. For MOS2 CNT, it's a 7.9 in 10 power minus 6, one order low. But I'm okay with that, because still there is a room for further improvement. So that we went for further analysis, where we did same single cell test, where we use this NaFn 117 4 centimeter square and 0.2 milligram iridium for anode and 0.2 milligrams MOS2 CNT as a cathode. Now we can see that the current density improved quite a lot. Earlier it's for 65 milliampere, right? Now I decorated only MOS2 over a CNT top. So now I am able to reach around 240 milliampere at steady state value, and we operate the cell for 400 hours continuously. It's a very important long-term operations conditions, because we need to use it for long-term hydrogen generation. So now I have cell data of 1000 hours of operation. So it looks quite good for me. 250 milliampere is quite good, because it produces 1/4 of the platinum value. But still the CNT cost is a little bit higher. But we want to replace the material with our own carbon, which is going on in our laboratory. So this material is stable. What I am saying is, this material is stable. The MOS2 is stable. We can able to use them in large scale hydrogen production if you prepare a very good catalyst for a large scale quantity in our laboratory. So this conclusion, first part, MOS2 is an alternate material for electrochemical hydrogen production. Shape engineering is now affecting the surface morphology by the time beyond surface area. So MOS2 geometry plays an important role, which is exposing active sites for the hydrogen generation. Further improvement of conductivity can be done by MOS2 by decorating over the CNT, so that we can go for a further enhancement of the activity for the single cell analysis. So in continuation, so we know that MOS2 is a semiconducting material, but as I said earlier, there is a one more system, 1T MOS2. It's a metallic form, but the stability is not that much up to the mark, right? So we want to go in this direction also, because it's we know that it's a 2D layer material. The distance between two layers is 6.5 Armstrong. So if you go more than 7 layers of the MOS2, it becomes like a bulk material. Its band gap is around 1.3. So there is a we know that the basal plane is highly stable but highly inactive for HCr. But once you go for the activity of the MOS2 are mainly from the MO edges, because metal centers. So where the sulfur edges are inert, because delta GH, the adsorption energy for MO is 0.08 electron volt. For S edge is 0.18 electron volt. So excess energy required for the adsorption. So but the uncharged sulfur atoms are located in the edges of the MOS2, act as active sites also, because it has the small delta H value. So there are crystal phases, two phases. There are 2H and 3R found in nature, semiconducting. The stable H means hexagonal and R means rhombohedra. 1T phase is discovered from 2H, it's a metallic phase. It's called a tetragonal, right? So normally the 1T at room temperature converts back to 2H because the metallic immediately converts to semiconducting. So this is highly around 30 degree, it will automatically converts into phase conversion. So if you go for efforts made over the MOS to improve HER, because people are thinking you don't want to go for decoration or other deposition composite material. Along with the MOS alone, the nation material alone, how to improve the activity. So there are many studies are there. The inert sulfur atom can be doped with the foreign atoms like cobalt or nickel that can be activated. Increase the number of active sites by varying the morphology that can be done. But improving the conductivity of the by growing MOS on carbon active sites, that's very important because after some time the MOS will be detached from the carbon so that the activity will be going down. So the forming the core shell, that's also possible because you can take one core and then you can form the shell as a MOS material. That will be having more activity because the conductivity will be different. So that's also possible. And interlayer variation, as I said earlier, the layer distance 6.5 can be enhanced by putting other alkyl ammonium ions so that we can have the more conductivity and more edge sites for hydrogen production. And the number of layer reduction can be done because if you decrease the number of layers, the conductivity of the material will be going up. Similarly, the creating defects over the surfaces can also possible, but also active for HCr. But the problem is with these immense effects, even though the activity has been enhanced, they end up with the lesser impact on the HCr activity because the lack of the density of the active site, because number of active sites per unit volume is very low. So they cannot able to reach a particular level. So that the role of 1T in MOS2. So the 1T phase, how it's very important. The 1T phase shows enhanced catalytic activity in HCr when compared to 2H. Electrochemically active basal planes and edge planes towards HCr. Density of active sites increases because 1T has more density of active sites and increases the electronic conductivity 10⁷ folds higher than 2H phase. That's very important. So this 10 lakh times of improved conductivity alone have its own dominance over the activity. So and then hydrophilic in nature. Hydrophilic means water loving nature, so that the electrolyte will be penetrating easily throughout the MOS layer so that you have more active centers. So therefore the phase engineering is a way by which the density of active sites can be enriched, and then therefore it is highly desired to work on 1T MOS2. So but the problem is 1T MOS2 is synthesis of MOS2 with the enriched phase is very limited because we can go only 20% or 30% of 1T phase, remaining 70% will be your 2H phase. And then one is to whatever the formation of 1T phase, within half an hour or 1 hour, it will back converted to 2H phase. So the two problems are there. So we need to avoid them. So how to do the things? So how the initial people are doing, there are two methods. One is top-down approach, where the lithium explosion can be done. Especially battery people are using this material because they need a large quantity of 1T for their battery application. They use organic medium and then unwetted lithium for making a single layer of 1T MOS2. But this is a scale up possible, but only thing is the undesired organic solvent, especially unwetted lithium, is highly phosphophoric because it will catch immediately fire. Everything should be done in a fume couple. It's not possible for using go for a kilogram scale of production for fertilizer application. So it's not possible. So the bottom approach are there, aqueous based medium. So one is the enrichment of 1T phase is very minimum because we can use this aqueous medium, but now 10% will be grown or 20% will be grown. We cannot grow over this. And then reproducibility is very low. It's very important thing is whatever the ionic components what you are placing inside, it affects the growth of the 1T MOS2. So the reproducible resist may not be attained the same. And then third one is the large scale production is still problem because we are producing only milligram level in this based on aqueous medium. And then room temperatures or storage stability is very important because you can prepare 1T MOS2 with 30 to 40%, but if you store it at 25 degree, the stability will be very low. Within 2 days or 3 days, you will convert back into 2H phase. So therefore, still there is a need for a facile method to achieve the maximum formation of 1T phase with constant reproducibility. So very important thing is you have to produce 1T phase in 90% or 95%, but similarly the reproducible results should be there. If you use the same volume or same amount of precursors, you have to end up with the same amount of 1T phase and same quantity of material. So that's very important in this case. So this is what we are developed here is template driven phase selective formation of the 1D MOs to nanofor for hydrogen evolution reaction, because we used a template, a nanoscale template, to grow the material inside the template, and then after that we demolish the template and then we recover the material. So this is a template based process. So in this case now we use silica SiO2, where no well-known material is S15. It's a commonly available material for any industrial scale application. So we prepared this material based on our chemicom paper in our laboratory, because we need for more than 5 to 10 grams per single batch. So we need to reproduce the same results. That means your S15 should be having a identical property. So that you have to have your own methodology to produce a large scale S15 in your laboratory. So very important thing is the first step. So we prepared a TOS based method, where we use fluoronic 123, HCl and H2, and then we used hydrothermal at 100 degree for 24 hours, washed with ethanol and calcination at 500 degree. So this pore size produces around 10 to 15 nanometer, and then act as a nano reactor, and then the 10 nanometer pores are providing a confined space to grow our own MOs to nanoparticles powders in the inside the material. So this is the characterization of the S15 what we prepared. So we need to confirm whether the material is available or not. The wide angle shows around 25 degree for the amorphous silica, and the low angle peak at 100 and 110, 200 perfectly reproduced by the same material. So the SEM and TM analysis shows that the material is in very good morphology as well as the very good purity, because the nanos channel should be very completely pure from the other surfactant materials. So we got it completely pure S15 using this method. So we characterize by using BET analysis, because the BET should be confirmed from the material. So its surface area should be 682 mm, around 700 should be there. So the type is type 4 isotherm, which confirms the mesoporous nature, and then pore size is around 12 nanometer. Pore size distribution also gives a very good uniformity in the pore size and having a maximum pores of the 12 nanometer size. So the reproducible data is there. So now we are going for the preparation of 1T MOs inside the S15, where we took two type of precursors. The first one is sodium molybdate, because we want to establish a method based on the precursor also. So we used sodium molybdate dissolved in S15, and then we used the thiourea and stirred for 24 hours. Now the S15 combines the MO inside, so it trapped the MO inside, and then after that we went for the hydrothermal at 200 degree 24 hours, and then the MOST is formed inside S15. After that we used 0.5 molar percent HF for the etching of the silica. So now we are removing the silica by etching it. So that's a process what we are employing here. So this is S15. So we filled the MOST inside. So form the MOST inside, and then after that you replace the S15, and then you are getting only the S15, the MOST alone. So in the first case we are getting the hydrophilic metallic form of 1T MOS2. That's called SN-MOS2. Without S15 also we are doing, because we want to compare it. So sodium molybdate in thiourea, so it gives NMOS2. That means sodium molybdate MOS2. This N means sodium molybdate MOS2. So this is a hydrophobic semiconductor. So in the case of S15, we use if you use S15 as a nano cages, you will produce a hydrophilic metallic. But if you are not employing S15, you are producing a hydrophobic part. So that means it's a completely 2H part. So that similarly we use the ammonium molybdate as a precursor and thiourea. So in this case also we are getting the hydrophilic metallic first inside the S15, and then without any S15 you are producing a semiconductor material in the MOS2. So this is called as a sodium molybdate MOS2, and then this case of ammonium molybdate MOS2. In the case of S is S15, this is ammonium molybdate, this is pure ammonium molybdate SPF2. So if you go for XRD, we can see that in all the cases we are producing MOS2 with a good crystalline nature, but only thing is in the case of ammonium molybdate case, the slightly change in the peak position is showing that there is a slight entrapment of the ammonium cations in between two layers. So it's confirmed from the XRD shift, and all the other things are very well matched with the acid data. So that all the cases we are having MOS2 inside. So the Raman analysis produces the very important phase where the 1T MOS2 having a fingerprints in the region of between 300 to 100. So where you having very important peaks of E1G and J2 and J1. Other things are E2G and then A1G. So in case of only 1T MOS2, these phases are appeared. But other cases of MOS2, where the 2H case, you don't have any kind of peak here. So this very well differentiation peaks are only through the Raman analysis, because the Raman is very important to analyze the both metallic and then 2HMOs2. So if you go for nanostructural analysis, you can see that in all the cases you are forming a MOS2 with flower morphology. As I said earlier, these materials are layer structure. Once you demolish your SB15 silica, the layers comes together, they forms aggregated flower like morphology. But only thing is the distance between two layers is 0.65 in the case of 2H phase. But once when you go for 1T phase, it's a 0.93. So it's the difference is due to the metallic form entrapment of the other ions. So when the XPS studies only the we can do the quantification of the both phases, because no, the binding energies between the 3D MO3D by 2 and then this one is they are one electron volt far away, because you can see that 1T is having a less binding energy than 2H, because the metallic form having a less binding energy. So from the binding energy value from the peak area under the peak, we can able to quantify how much 2H you have and how much 1T you have. Wherever you are using sodium, sp15, you are having an enriched 1T phase, and then wherever you are using without sp15, you are having 2H phase as a dominant. So that case, no, you are having a difference in their MOs2. Similarly, in the case of ammonium precursor, we are having nitrogen 1s peak, which is now around this area, around 402. We can able to trap ammonium ions. In the case of ammonium molybdate, we can be able to find the ammonium scale also. So if you go for electrocatalysis studies, where you are going to compare all them together, and then for the PT, it starts around 0. It's no. For 10 milliampere, it took 90 millivolts as a over potential. But when you go for 1T phase, you can able to see that the 2H phases are inferior for hydrogen evolution. But in the case of 1T phase, you can have 252 and then 263 millivolts as a 10 milliampere current density region. So similarly, the PT produces a 30 millivolts lower TEFL value when compared to the other material, but both 1TMOs2 produces 45 and 50, other are producing 60 and 70, and then which is directly coming from the electrochemical surface area, which is measured from the non-Faraday region, where you can able to see that the 1T phase, due to hydrophilic nature, they have a large surface area, almost 10 times higher surface area when compared to 2H. So similarly, you can see that the RCT value is less than 1000 for 1T, but it's all very close to 6000 for 2H. So the conductivity part is diminished in the case of 1T because purely metallic. And then the best material SNMOs2 produces the 10 milliampere current density over 10 hours of long-term operation without any deviation. So the hydrophilicity also, you can see that the 1T cases are more hydrophilic and 2H are more hydrophobic. So this is the best activity, and then the stability also we have seen. The material what we prepared in our laboratory, after 30 days, we tested for both XRD and Raman, and even XPS, we measured it, and then the stability is very good. And then we have nowadays, we have 1 year old data. So after 1 year, the materials are very stable. So this is our conclusion. So this work now selectively forms 1TMOs inside the S15. It forms 90% 1TMOs too. And then it has we produced the material over 14 times in our laboratory. We repeated the same experiment with the same quantity of material. It produces reproducible data. And then now the storage stability of 1TMOs at room premises now. We tested for 30 days, and then it has very good activity and then stability. And then highly safe environmental procedure, this one, with upper space material. And it has a very stable material, so that this methodology can be employed for any other materials, and then methods were for large scale hydrogen production. So with this, there's a long way to go. We want to establish the method for the hydrogen generation green method. So we will be publishing the data in near future. So this is my acknowledgement. I would like to thank our directors Ramesha, Kalachali Madam, Vajan Manpillai for their support, and then finance support from the CSIR, DST, UKRI, and ISCTF. And then our group students and postdocs. Without them, I cannot be able to present the data here. And then I thank our collaborators, BRC, Bombay, EXAFS, and the Nanoscience Institute, Argonne Institute of Zaragoza for the SCM measurements. And thank for their organizers for funding sources. And thank you for your organization. Thank you.
Thank you, sir, for your wonderful talk. If you have any questions, you can post.
Yes, thank you for a nice talk. It's maybe I missed it. Is it KS1 or K1 phase?
One T phase.
20 phase.
Yes, yeah.
It's unstable.
Yes.
It's converted.
Yes.
But then how did you make it stable with
It is more than 6 to 7 layers. The number of layers decides the stability. We understand
so
it.
the template help to get more layers?
One way. And then without the template, it's not easy to form 90% in the solution.
Yeah.
Because there should be a space where the confined space should be there. Allow the precursor to go in and form the 1T phase alone with 6 layers. Then will be stable, and then you can demolish the SB15, then you can take it. So the nano cages, the volume, the 10 nanometer
Template is
also, yes, effect.
phase to
Yes, yes.
Thank you.
Yes.
Any other questions? Okay, if no more questions, we thank Dr. Sindil Kumar for a wonderful talk. Thank you very much, sir.
Thank you very much, sir, for sharing your deep knowledge about with us. And I thank Dr. Sivakumar, sir, on behalf of the SWAP organizing team for serving as a session, sir. Now I would welcome to invite Dr. Sivakumar, sir, on the stage to honor the Dr. Sendil Kumar, sir, with a memento. Now I would welcome to the Dr. M. Rajan, sir, on the stage to honor Dr. Sivakumar, sir, with a memento. Now I would welcome to all our distinct guests on the stage. Now we move on to the session brainstorming. Share your knowledge is a way to achieve immortality. So that this session is a great opportunity to interact with the immediate scientist. So that I request to all the participants interact with the immediate scientists and the professors with enrich your scientific knowledge. Now Dr. Sachin Mordi Chavan will lead the session now. Thank you.
Yeah. So I invite speakers to join us on the stage. Trolls will come. Yeah. Don't want to go. This is an open discussion session. So if you have any question related to the workshop, catalyst, electrocatalytic, photocatalytic, electrochemical, photoelectrochemical, please feel free And if your question related to the education, PhD, whatever that is boiling in your mind, new ideas, how we can solve the problem of global warming and hydrogen production and scale the hydrogen production at the required speed, please feel free to ask. Remember that we will leave soon, so you don't have chance to meet us again so soon. So if you have a question now, take your chance. I can start here, give a little bit warm up. Yes. So hydrogen, we need a lot. Yeah. If you want to decrease the CO2, it's almost like a 58 billion tons of CO2 is produced. And if you want to get zero, think about how much shift we need to do that energy. So thinking about India energy need, which technology we should focus? Because when I think of a big country, we don't have energy as only challenge. We got other challenges also. Population rise means food, energy, agriculture, land will be used. So all those things need to combine. We will have a lot of waste produce. We need to manage that waste also. So looking at overall all this picture in India, which of the hydrogen technologies are potential or have potential for Indian energy sector?
You have prepared something, but I think a mix of energy is important, not only one technology. Mixed energy means what the country actually possess. Attempt to make the population according to the growth of population. And what else? Development, education, and all this stuff. I think it's very important. Great job.
I open the session with a question. Considering India as a big country and with the population and the other challenges that India will have with respect to the food and water and what waste that India will produce in the future, and we want hydrogen. And so there are different technologies to produce hydrogen. So which technology India should take advantage or has a potential for India, considering the geographical situation and the climate that is in India now? That was the question. Sir, I go from also.
Oh, that is a difficult question, but when I think about hydrogen from my perspective, I am sometimes thinking, why do we want hydrogen? Is it because you need it locally to solve your energy situation, or is it because you want to make a big impact on the world emissions of CO2? And for instance, if we take Norway, we have enough energy, but we have a lot of fossil energy that we don't need. And then the best thing we can do for the world, in my opinion, is to make blue hydrogen, store the CO2, and export this hydrogen to countries that need it. I guess India is in a different situation. You want more energy yourself. You need probably lots of energy, and you have, okay, I'm thinking quickly, you have a lot of solar energy, more than enough, and you need to store it in order to use it efficiently. So then I guess, okay, you want to make hydrogen, but you also need to store hydrogen. then maybe the question is next, what do you here see? How can you store hydrogen? Is there any way except just tanks and things like that? Is ammonia, for instance, of interest to this fly likes me? This is ammonia of interest to India as a way to store hydrogen? And maybe that is enough.
Yes, I agree with the browser. Actually, in India, this is a very broad geographical regions. So especially the solar energy will be a better the source of India. This one.
The counter question from speaker here or from the stage is storage. Do you hear in India about hydrogen storage, and which are the potential technology India is looking into? Have you heard about hydrogen storage?
As far as I know, hydrogen has a high energy mass density. So, isn't it true that for storing it, we need really big containers? So, even if we are trying to utilize it in vehicles, where are we going to store that big tank to run the vehicle? Because the vehicle would be small and the tank would be bigger. So, isn't that a problem if we are trying to utilize it for vehicles? And even if we are trying to store hydrogen, isn't it true that the cost would be so high that it won't be commercialized as far as the people who are like the not so privileged section of the society? How are they going to manage it?
I think the question, it's, you want to say it before I say it? So to use the solar energy, which will not be continuous. So there will be peak hours where there will be lots of solar energy and people will not use that much. So what we do with surplus energy? So if that surplus energy is stored in hydrogen, then we can use it for different industry. If that surplus energy is stored in the batteries, so we can, when there is a low sunlight, we still have constant supply of electricity, because then we store the electricity that was produced. So hydrogen in a way can be considered as a one storage media of sun, solar energy, and battery can be also considered as a one way to store energy. Yes.
I totally agree with you, and it's a very good comment because it makes me think. I was a big fan of hydrogen vehicles for people, and maybe it will still come true, but I would say don't think about it. It will be the battery vehicle that will be for normal people, and it is a way to store energy. So for the vehicle, you don't need to worry about the big tank and all of that, because that's a small amount of energy, and the battery is perfect for it. So the battery vehicles actually help to store the solar energy and even it out. So that is solution for that is clear. You need a good electrical grid or many local solar plants, but that is solved. But for the big vehicles, the heavy trucks, for the ships, for the trains and all of that, sooner or later, it has to go away from fossil and it has to find something else, and that will be hydrogen or ammonia. So then the question is, where do you store that when you want to use it? And I guess the last thing is, what else do you need energy for, by the way? In India? In heating? No.
No.
Cooling? Yes. You need to cool when the sun shines? Maybe your problem is not so big as, as in cold countries.
I would like to add some comments, right? I think one of the biggest challenges is to store the energy. You have to look at the wind energy. There are a lot of wind. I think people are not able to store all this energy that winds can generate. So we need big batteries. What kind of batteries? So, as solution, for example, the flow battery. You can put the size of a water pool, and then you can probably store this kind of energy. Now, regarding hydrogen, 90% of all hydrogen produced in the world is not used for vehicles, it's used to make chemicals, right? So, for example, urea or something else. So, what would be interesting, this is my personal opinion, for vehicles is to produce hydrogen on site. All the hydrogen we have are stored in the chemical bonds. That is the best way to store hydrogen. The problem is that we have to use artificial photosynthesis at will in order to have the hydrogen, and that is a big challenge. Anyway, that's the problem.
That's a very good comment. I attended a meeting organized by Ministry of Energy, Indian, and they created a task force. And the focus on hydrogen is not a mobility at all. So production of fertilizer, chemicals, and metal industry. So India is targeting these three sectors that you probably not heard. So, and the current technology, steam methane reforming, for 1 kilo of hydrogen, 9 kilo of CO2 is produced. That's the current ratio. I think, and then
1 kilo hydrogen, you have to consume 9 kilogram water.
yes, that's also for the yeah, but it's also with the electrolysis. The ratio is quite like for 1 kilo of hydrogen, you need at least 5 kilo of pure water.
Yes, but then you get 9 kilos of water back when you
Burn it. Yeah, that's true. So the so the three sectors that India is focusing on, those are the, as I mentioned, the chemical industry, that's a consuming, metal industry, and yes, because there is also a lot of hydrogen need, because urea production, you natural gas, and then it produces CO2 also there. And India has planned a corridor, hydrogen corridor, that's called, it will be from Mumbai to Delhi. So there will be demonstration on vehicle, but I guess these are the demo plant. I think the main focus is other side. So this question I asked already before, with the population growth, the bio waste also will be produced quite a lot. And the bio waste, if you pyrolyze, you can produce carbon and hydrogen. And carbon can be used for agriculture purpose, for enriching the land. So there will be process to go from bio waste to biogas, and the rest will be pyrolyzed. So this was not actually in a plan, but later I heard that there is also plan for using the bio waste and go for hydrogen. I don't know if there is any activity that you heard about biomass valorization for the energy sector, particularly with the focus in India. I think this will be big challenge in future, because at the moment municipalities are not doing it. It's a dumping. It's not treated or it's not produced. I don't know. How is the situation in Tamil Nadu? Is there a lot of biogas production in Tamil Nadu? No. I think you have a question. You wanted to ask something?
Sir, greetings, sir. In hydrogen, hydrogen and oxygen are taken, and water is produced electricity. But all hydrogen and oxygen are not completely produced into water. In that case, what is the factor which determines these molecules, these atoms could form water molecules, and these could form hydrogen back and unused hydrogen and oxygen? What are all the factors which determine, sir?
Maybe your question was some of the hydrogen is not combusted. I think in a fuel cell, what is not combusted is recirculated and used out of a fuel cell system comes no hydrogen, only water. But the question, we can take the question further. A huge hydrogen industry will lead to some leakages of hydrogen. There will be hydrogen coming out in small amounts everywhere. And to my understanding, hydrogen is a much worse climate gas than methane and CO2 and these if we let it out in large amounts. So I asked a researcher on this, will the problem of hydrogen coming out be bigger than the problem we solve? With hydrogen, we solve the CO2 problem, but is hydrogen a new problem? Similar, if you capture all the CO2, you will emit some amines, which are now used to capture CO2. And the clear answer is you must solve the big problem, because the emissions of these gases, hydrogen amines, is a small problem in comparison to the big problem. So my simple answer would be, don't worry about it. And using the hydrogen you don't get, I don't think it is a relevant question. Maybe it was not your question. And then you said, can something else form? I don't think so. Maybe I misunderstood your question.
If all the incoming reactant that the products are coming converted into total, that water is completely converted into water means it is a perpetual only, no, sir. So is it possible perpetual? I think the perpetual may not be possible. So some of the hydrogen and oxygen might be left. In that case, what I don't say that hydrogen is harmful, but in what case the hydrogen and oxygen is completely converted into water, and in what cases they are left out?
Which technology is giving maximum efficiency in conversion of? No.
Oxygen you take combined as a water. You are asking the commonly the reactions, hydrogen, water, and hydrogen, oxygen, and water formations. Yes, sir. Actually, the common water formation is the gas form of hydrogen and the gas form of oxygen only. It is come to the waters. So if it in the form of the gas, it is not a forming. It is not involving the water formations. Okay.
Okay, so what is the efficiency of fuel cell?
I don't know whether it is right or wrong. Actually, you see, we have electrodes now. In fuel cells, we have 2 electrodes, and PEM membrane, etc., is used. We have titanium plates as the electrodes actually, and the titanium plates have grooves, which is intricately carved, channels like a thing, narrowly constructed. And when we pass in hydrogen this side and oxygen that side, means it actually moves, so that the wastage of hydrogen or oxygen is avoided. And efficiency, what we get is more than 90, I think. So in that way, the wastage of hydrogen and oxygen which is coming out of the cell, unused hydrogen and oxygen, is minimized. It will be there, but it is not as expected what he told.
Thank you. Interesting.
The titanium anodes and the cathodes, no, it has grooves. It has grooves intricately.
Yeah, they are like porous transport layer. They are kind. Yes. So we are thinking about hydrogen one side. What is produced also? Second is the oxygen. And you know how much oxygen is produced for 1 kilo of hydrogen in the electrolysis process? Is it? 16 kilo or 8 or 9? 8 kilo more. Yeah. So for 1 kilo of hydrogen in electrolysis, you produce about 8 kilo of oxygen or 9 kilo of oxygen. What are we going to do with oxygen? Maybe I'm wrong. So what are we going to do with oxygen? What kind of application we can use that oxygen for? And oxygen is it's difficult to handle. So, and the second point that professor mentioned, that hydrogen, when it leaks and it has more greenhouse danger or potential greenhouse effect. Do you know why that happens? Why hydrogen is more has a higher greenhouse? So I think this the depletion of ozone, and then the methane concentration, because methane is actually helping to maintain the ozone layer. And if hydrogen comes in and a hydrogen consume that one, then they will have more methane. So atmospheric level of methane will change, and you have indirect effect that there will be more global warming effect. So leakage, of course, is not that dangerous, but it should be avoided to maximize the use of energy. So what are you thinking if we produce hydrogen and more oxygen? What are we going to do with that oxygen? Some companies they talked about, during COVID time, what we needed, oxygen cylinders. So one the companies they showed medical application is there. In India, there was really lack, so immediately we had to install lots of pressure swing adsorption in many places to separate the air and give the oxygen. Yeah. So one application is medical, but I don't know. It will be not. I hope there will be no another pandemic, and we don't come into that situation where we need oxygen. But what will be the other application?
Yes, I agree, and I think what India needs is entrepreneurship to get business going. Like if you do electrolysis of water, you can also sell that oxygen. But that reminds me of something else. We scientists have a tendency to say all the time that everything is so difficult, it's impossible, it doesn't work, it's not efficient. We have to do our research, otherwise it is hopeless. But everything we talk about can be done by existing technologies easily, and has been, for instance, hydrogen has been done for 100 years. It is extremely common chemical to make hydrogen, can be done by reforming and by electrolysis. In Norway, we have electrolyzed water for 100 years to make fertilizers. So it's not difficult, and alkaline electrolyzers are the most efficient electrolyzers. PEM electrolyzers are also good, but they need iridium. If you want to make oxygen and sell the oxygen, we must be aware that there are fantastic membranes that can separate oxygen from air, or distillers, cryogenic distillers that can do it. It's cheap, it's easy. The oxygen problem during COVID was not that it's difficult to make oxygen. It must have been the infrastructure of transporting. So let's be realistic, because what politicians need, I think, is some kind of push to do things, to do something. If you want to make hydrogen and want to have a better energy system, they should implement the technologies that already exist, not wait for us to develop better technologies, I think. So let's know our responsibility as scientists, and not only make trouble, but also help to make the right decisions while we are improving the technologies for the future.
I totally agree. Implementing the existing solution will also allow us to learn a lot around what we need to have in a place. Without going out of the house, you will not see what is out. So you need to start working on it, and then while doing that, you learn quite a lot. Building, I mean, it's the same experience you have probably when you read an article, everything sounds good, but when you go to the lab, then the challenge is what are the steps you have to do. And you learn quite a lot while doing it, not just reading the manuscript. So yeah, I think it's the same. And the entrepreneurship is very true. So I teach at the engineering university there, and I'm teaching process engineering at a bachelor level. My education was in natural science, but I did research in process engineering. I think that all chemistry student or material science also should go one step ahead and think about whole process, not just stop at the material level, but try to think about the whole process, how it will be done, the energy required to do the process, mass balance, energy balance, safety. It's it that will give you, that will train you to think about which solution is the best. Because at the low TRL level, there are lots of fancy things. But when you get this complete picture of the process, then you see that probably is the most mature technology going to be in the future. Okay, I'm not talking now more. More questions from you?
Can I ask a question to the audience?
Yeah.
Which is the most important technology in India, biomass or solar energy? I'm just curious.
Okay, how many things solar? Raise your hand. Bit more, so we can say. And okay, biomass. Okay, solar is leading now. Did you say that?
We already have many plants, many solar plants and all. We have that technology is already exists here. But in biomass technology, we are still the scarcity of in India. We have a lot of biomass productions here. But the problem is the resources. We are not properly not using the resources, biomass resources, because we have a lot of biomass resources. But the problem is when we are taking to the pyrolysis, each biomass possessing the different properties. So it will be very useful for in which domain, like battery, supercapacitors, and very various energy storage and conversion technologies is there. We have to choose which one material is apt for this technology. And also another thing in my concern, we are all talking about this hydrogen production, conversion and technologies, and in India what we have more about the batteries and capacitors and hydrogen production. These three storage, conversion and production part, we have to concentrate. Which one is suitable for our electric vehicles, and which one is suitable for in other kind of applications, and hydrogen production storage is suitable for and different applications. We have to systematically distinguish that, then only it will be good for us. And also recently we have many battery production technologies here, like Ola and Godi Electronics. Many technologies are just now they are opening their battery productions and also fabricating technologies here. So in this way, if we are thinking, means it will be very easy to address the problem. For electric vehicles, we have set of batteries and battery systems. It is integrated with supercapacitors, means it will be useful for regenerative braking and startups, and immediately moving to one place to another place. And we have limit some put some certain limit, this kilometer to this kilometer we can use this battery for transportation application. Like energy for hydrogen storage, we can use for mass production for plants. Like that, if we are distinguished, means that will be useful for us. It's my opinion, not about all.
Okay, some more? I think they are interested.
Okay, I think it's a little bit difficult to say things in a spontaneous way. Well, now sitting here, I was thinking when I was young, I read a book from Bocris. I don't know you have heard from Bocris. Was one of the good electrochemists, we would say, in electrocatalysis, and he was the guy who wrote in the 70s The Economy of Hydrogen. You can read this book, okay? I was fascinated at that time. I was maybe 20 years old, something like that. Anyway, so what's new? Why nowadays we are discussing hydrogen? Only because the politicians say, oh, hydrogen is very important, or only because that is the way to get some money to do work at the lab? I think this is the problem, right? Because hydrogen technology or electrolysis is an old technology. because that was already done in alkaline made using steel as electrode. That's insufficient. Now, why we want more hydrogen? Just because CO2 concentration is increasing in the atmosphere, only because we are going to get 1.3 degrees by the end of the century? Tell me, what is the problem? Right? So that is the situation. Now, if we want to store hydrogen, we solve one problem and we create another one. Hydrogen, there is a phenomenon that one should think about, the hydrogen embrittlement. It goes everywhere. And that is also dangerous in the system. Nobody talks about that, but this problem exists. So please be aware about the hydrogen embrittlement.
Yes, so hydrogen can be stored in a different form as a gas, pressurized, then the embrittlement. Yeah, then metal hydrides, metal borohydrides. That's a solid storage of hydrogen. Conversion to ammonia. Ammonia, we have been using ammonia for a long time. Fertilizer industry, the infrastructure is there, experience is there, technology is there. So less challenges. Methanol is another carrier. They call liquid hydrogen carrier, I think. So also there is a good experience and large experience with using methanol. But again, there will be the carbon that is associated with that. So there are different, because when we think about Norway, in the focus is maritime, because we shipping in business is big in Norway, and country has made a clear vision. Where do we want to cut the emission? So in that way, India also probably will come up, and not come up. There is probably plan in the presentation today. You saw there was a green hydrogen infrastructure. So Nitin Gadkari has made an announcement that there will be a lot about hydrogen in India. So they are moving. Lots of battery manufacturers will be also coming in India. Any other question or? Okay, we take it.
Sir, both hydrogen and solar are needed, but in comparison, if the efficient solar is more stabler means, then what are all the advantages and disadvantages of this fuel cell when compared to solar? Next one, few are saying that the water produced from the hydrogen cell that will not be essential for a drinking purpose directly. It might have get added. They are saying, is it a myth or a
Actually, the formation of water in the fuel cells. So as we know well, the groundwater or any other the RO water, it having the number of minerals. And if in the fuel cell water formation, it is not the type of the minerals and other constants. So that one we cannot able to drink.
And the first question was which is better? Yes, whether solar or fuel cell. But I think they are made for different purposes. I think so. You can take a solar and store the energy either in a battery or in a fuel cell. But they have made for different. One is a stationary. One could be mobility. Based on their efficiency, they will be used in different sectors also, because the energy requirement is different. So at a home, if you put a solar roof, get the what you call the battery or some kind of capacitor, you can store electricity energy and use in the evening. But factory will not do that. Then they will need a lot. So that's different application. That's where it comes. Okay, this was good, quick, bouncy discussion. Nice. I thank you all for being so sporty and joining in a short notice. And there is one more question. Shall we take? One student want to ask question. One student have one more question. Good.
Sir, actually, different methods to produce hydrogen that like photocatalytic, electrocatalytic, or photoelectrochemical. So while doing the reactions, that how to measure how much hydrogen is produced? That is my question.
How to measure? Yeah. So you use the instrument to analyze the what is coming out in GC, and you will know how much hydrogen is. Yeah. You can use it definitely. That's a good.
So that the answer is volumetric. We measure it by the volume of hydrogen, which is what the flow meter is measuring.
Yeah. And if you want to do quantitative analysis, because if it is coming mixture, then you can analyze with the GC and yeah.
From an instrument is connected to a flow meter, and we can measure how much of liters or milliliters of hydrogen is
Yeah. Yes. That's Madam answered that question, I think. If you know the total flow that is coming out, and yeah. Okay, good. Let's stop here. Please join me to thank all the chairs. Yes.
talking about carbon dioxide. No, there is some, one important thing called carbon dioxide sequestration. We have not mentioned that, I think, in the session. Huh? Okay, so we want to take up carbon dioxide sequestration also in the next, upcoming session. Yeah. Thank you.
Thank you very much, sir, for sharing your precious words, ideas with us. It will truly helpful for your scientific career path. Now it's a time for a tea break. Let us all assemble back here at sharply 4:15. Thank you.
Mm.
respective presentation within 10 minutes. Please stick on to the time. Chairperson of the session for oral presentation, Dr. N. Krishna Kumar sir, School of Physics, Madurai Kamaraj University. Dr. T. Arokyadas sir, School of Physics, Madurai Kamaraj University. Dr. J. Annaraj, School of Physics, Madurai Kamaraj University. Thank you.
Good evening to all. First of all, in this oral session, I call the first participant. Mrs. Sivagami Rajaram.
Good evening to all. I am Sivagami, working as an assistant professor in the Department of Physics, Tiruvallur College, Pavanasam. I am going to talk about nanostructured iron and platinum on multi-walled carbon nanotube, efficient catalyst for transfer hydrogenation of carbonyl compounds and aerial oxidation of alcohols. Next. This is for my plan of talk. Introduction, synthesis technology, experimental work, characterization, and finally I conclude my results. Nanoscience is the study of fundamental principles of molecules and structures, at least one dimensions roughly. This is nanosynthesis technology. Preparation. Preparation of iron and platinum decorated multi-walled carbon nanotube. First, I functionalize the multi-walled carbon nanotube using sulfuric acid and nitric acid is 3:1 ratio. For 3 hours and 60 degrees Celsius. First, I functionalize the multi-walled carbon nanotube and create the functionalized groups, carboxylic, hydroxyl groups like that. Then I take 0.1 molarity of ferrous sulfate heptahydrate is dissolved in 50 ml double distilled water. Then I add 10 ml of ammonia solutions in the solution. Then these mixes were stirred at 3 hours for 60 degrees Celsius. And finally, I got iron decorated multi-walled carbon nanotube. After that, I take 5 mg of platinum chloride. This platinum chloride is dissolved in ethylene glycol. And these mixes were stirred in 2 hours for 210 degrees Celsius. And finally, I got iron and platinum decorated multi-walled carbon nanotube. Next one is confirmation. The crystal structure was analyzed by XRD pattern. The first pattern 002 is functionalized multi-walled carbon nanotube peak. Then second one is platinum decorated multi-walled carbon nanotube is 111, 200, 220, 3111. These peaks are platinum peaks and 002 is multi-walled carbon nanotube peak. So I confirm platinum is incorporated in the carbon nanotube. Then third one is iron and platinum decorated multi-walled carbon nanotube. The peaks is 002 and 002 is multi-walled carbon nanotube peak. Then 111 and 220, 311 are platinum peaks. Then 211 and 220, 022 are iron peaks. So I conclude iron and platinum are successfully incorporated in the multi-walled carbon nanotube. Then the crystal structure was analyzed by using D by Skinner formula, D equal to 0.94 lambda divided by beta cos theta. The estimated average crystallite size is 38 nanometer. This is the SEM image of functionalized carbon nanotube and iron and platinum functionalized multi-walled carbon nanotube. First one is functionalized carbon nanotube image. And then the second one is iron and platinum nanoparticles decorated multi-walled carbon nanotubes. This image clearly shows that iron and platinum nanoparticles are present in the SEM image. Next one is STEM image. These are the functionalized carbon nanotube and iron and platinum nanoparticles decorated multi-walled carbon nanotube carbon nanotubes. The second image shows that iron and platinum nanoparticles are present in the sample. The estimated average particle size is 50 nanometer. These are the catalytic activity of iron and platinum decorated multi-walled carbon nanotube. The efficiency of the sample was analyzed by gas chromatography experiment. These are the efficiency of the sample. These are my conclusions. Iron and platinum nanoparticle supported multi-walled carbon nanotube were prepared by simple chemical method. The fabrication process includes the chemical modifications on the surface of carbon nanotubes by acid treatments and the subsequent depositions of iron and platinum bimetallic nanoparticles. The morphologies and structures are characterized by XRD, SEM, EDAX and TEM. Initially, the reaction conditions were optimized, then the scope of the catalytic system was extended with a wide range of carbonyl compounds.
Thank you very much, Ma. In our XRD spectra, the 002 peak is completely absent in your composite. What's the reason? In your composites, this 002 peaks not present in your composite. Only Fe and platinum is present. First composite.
Pure functionalized, sir.
Yes.
Second one is platinum decorated
okay.
carbon nanotube. Third one is iron and platinum bimetallic nanoparticles decorated multi-walled carbon nanotube.
So why that peak is absent in our composite? This 002 peak.
Present all the two compounds.
Oh, இங்க scale மாதிரி இருக்கா? Okay. I call upon the next speaker, G. Dhanalakshmi, to give a talk on structural elucidation and computational analysis of a novel sulfonamide compound.
Good evening, sir. So my talk is on crystal structure and computational analysis of a novel sulfonamide compound. So here I have taken the benzene sulfonamide compound, which is an organic compound. It has more application as antibacterial, anti-tumor and anti-thyroid properties. And these benzene sulfonamide, they are usually called as sulfa pills, and they are an organically important class of drugs. So here we have taken this benzene sulfonamide derivatives and the properties were studied, and here we have used the single crystal XRD, and I have done the Ischfield surface and energy framework analysis of this compound. So the sample is prepared in the usual methods, and this is the schematic diagram of the title compound. Actually, I have solved the structure of this compound. That part I have done. So for this, I have taken the crystal and I have given it for the intensity data collection, and the reflections of the crystals were collected, and the structure was solved using the ShellX program, and the geometrical parameters and the figures were drawn using the program Parsed and Mercury. So this is the RTEP diagram of the title compound, where we can see that it exactly matches with the schematic diagram. And this is the details of the experimental diffraction data where we can find the empirical formula and the crystal system and the lattice constants and the volume. So using the single crystal XRD data, I could conclude that the geometric parameters of the title compounds agrees well with the closely reported structures, and the benzene sulfonamide rings of the compounds, they are almost orthogonal to the indole ring system, which can be identified from the dihedral angle, and which shows they are equatorial oriented, and the torsion angles indicates that they are anticlinal to the indole ring system, and the chlorine atom which is attached at the C20 location tells that they are also equatorially oriented. And this is the packing of the molecules, which shows the CHO interactions, and this is the hydrogen bonds of the title compounds. And we have also done the Hirschfeld surface analysis, which shows the intermolecular interactions. We have used the software Crystal Explorer, and these are the Hirschfeld surface diagrams. So the bright red spot shows the CHO interactions, and the other interactions appear as the light red spots. And this is the shape index and the curvature. So the red and blue triangles shows the pi-pi interactions, and this is the coordination environment, which was found to be 12 using the same Hirschfeld surface analysis. And this is the two-dimensional fingerprint plot, from which we can see the various interactions. These are all the percentages, and also I have done the energy framework analysis. So this is the energy framework, the Coulomb energy, the dispersion energy, and the total energy frameworks. So this is my conclusion. The single crystal X-ray diffraction studies confirmed the molecular structure. In the crystal, the molecules are linked by CHO and hydrogen bonds. The Hirschfeld surface analysis and fingerprint plots provide the nature of intermolecular interactions and percentage contribution from each individual contacts. And from the energy framework analysis, the dispersion components has a major contribution in the crystal. So I would like to acknowledge IIT Chennai for the data collections, and these are my references. Thank you. Thank you, sir.
Next, I invite Roshan Chandrapal.
So good evening, everyone. So myself, Roshan. I am doing my PhD in SRM University. So my title of my presentation is Construction of Zinc Cobalt Oxide, Nanobeads, G3N4 Nanosheet Heterojunction, Photocatalysts in effect of enhancing the photocatalytic degradation of environmental remediation. So the research background is environmental issues have been listed out as air pollution, noise pollution, as well as water pollution, thermal as well as soil pollution. So we will be concentrating on water pollution. So in water pollution, which is consists of pharmaceutical based pollutant as well as tactile based and microbial based and high metals precipitations in the water bodies. So we concentrating on water based degradation process. So the expensive procedure. So we have synthesized zinc cobalt oxide with combustion technique, which is now emerging technique in the formation of metal oxide based conduction. So we'll be using out zinc oxide preparation with respect to combustion technique, and graphite carbon nitride has been produced with respect to thermal technique by the annihilation of 550 degrees centigrade of melamine, and both has been composited with respect to the ultrasonication process under 1 hour of ultrasonication and heating process at 80 degree of in furnace. And these are the data. So we having confirmed the presence of zinc cobalt oxide and graphite carbon nitride from the XRD analysis, and the composite has also been confirmed through the XR analysis, where the mixture of phases of both pure zinc cobalt oxide as well as graphite carbon nitride has been present in the composite sample. So figure A shows about the pristine some formation of zinc cobalt oxide, which is noted as ZC, and the upper one Z3 and 4, which represent about the graphite carbon nitride presence. Figure B shows about the composite formation in three various percentage of zinc cobalt oxide presence in graphite carbon nitride, so which is 5, 10 and 15. And the figure C shows about the formation of FTI analysis with respect to the formation of functional groups over the material. So at the range of 500 to 1000, we can able to notice about the presence of cobalt oxide CO and O bonds, as well as zinc and oxygen bond formation, which is referenced with the pure of zinc ZC FTAR. And we are able to see about the tri-S retracing group of graphite carbon nitride preference under at the presence of in the range of 500 to 8000 range. And we have also obtained the optical property with respect to the UV analysis. So we have also obtained the absorbance spectra, and through which we have also calculated the tau plot, and from we can able to obtain the band gap energy, band gap level of the material. So out of we have calculated that for zinc cobalt oxide we have obtained at 1.38 electron volt, and for graphite carbon nitride it is 2.77, and we can be able to obtain a least of 2.351 electron volt for the highest composite sample, so which comes under the visible light region. These are the same images of our sample. So figure A, B shows about the pure graphite carbon nitride nanosheets, as well as B shows about the nano bead structure of zinc cobalt oxide. And this is the first morphology we have obtained with this particular zinc cobalt oxide, which was not reported yet. And the remaining C2 remaining sample shows about the composite formation of graphite carbon nitride with G3 and 4. And we have also calculated the elemental analysis for the highest dopant of zinc cobalt oxide in G3 and 4. And we have presented about the presence of carbon, nitrogen, zinc, cobalt, as well as oxygen with elemental analysis. And we have also calculated, we have taken the HRTM images of the particular sample. And through through figure F, we have calculated the interplanar distance, which corresponds to 0.248 nanometer, so which corresponds to the plane of 111, I think so. And we have also calculated the XPS analysis, through which we have confirmed about the presence of all the elements which we have used in the composite sample. So this particular XPS was being calculated, taken for highest dopant of sample, which is 15% of zinc cobalt oxide with graphite carbon nitride. And we have taken photoelectrochemical analysis and impedance analysis for the charge transfer properties. So we have compared with pure G3 and 4 as well 15% of graphite carbon nitride composite sample. So where we can able to see higher number of photocurrent property, so which implies about the charge transferring property from the valence band to the conduction band of the material. And figure B shows about the impedance spectra, where the resistance of the material after dopant has been reduced from the pure. So through which we can able to confirm what the charge transfer property is enhanced with respect to the composite sample. And PL studies, figure C shows about the recombination rate of the particular sample. So with the higher the intensity, higher the recombination rate, that's the principle. So with respect to the composite sample, we can able to obtain a minimum intensity of graph, so which implies about there is not much decombination of electrons to the valence band. So it has been retarded, and there are many electrons has been reacted to the surface of the material, surface of pollutant for degradation process. And we have also calculated the scavenger analysis. So scavenger analysis is generally to note about which radical is participating much in the reaction process. So we have taken benzoquinol, IPA solution, as well as EDTA. So which each one has a benzoquinol for superoxide formation, for superoxide retardation, isopropanol for hydroxide retardation, and ethylene EDTA for whole retardation. So through which we can be able to conclude that the highest degradation has been obtained with respect to BQ, because a scavenger is an inverse of percentage. So we are getting, if we are getting a lower number of percentage in the particular sample, so which retards the functioning of superoxide radicals, which shows about the highest participation of radicals in the degradation process. So we can able to obtain only a lesser number of degradation with the scavenger analysis. So we have confirmed about this particular test that superoxide formation, which is carried out in this conduction band of the electron, conduction band of material, has made a highest number of participation in the degradation process. So we have carried out this particular sample for two pollutants. One is colored one and is non-colored. Colored one implies rhodomin B, which is textile-based pollutant, and we have carried out this with the pharmaceutical-based pollutant. This colorless, which is CIP, which is known as ciprofloxacin. So majorly medical industries, we can able to obtain the ciprofloxacin. So only to a particular level it is not toxic, but due to the formation of excess number of medical wastes, it is huge. So when we are compared with this particular data with pure graphitic carbon nitrate and the composite sample, so through this particular analysis, we can able to see that within 60 minutes of time, we can able to obtain a maximum number of degradation with respect to composite sample for RHP, and for pure CAP, it has taken 120 minutes. We can ask a big. The reaction rate has been calculated with respect to the pseudo first order reaction process. We have taken C by C naught as well as the ln of C by C naught. So through which we can able to see that 15% of composite sample with the graphitic carbon nitrate has shown an highest number of slope, which enhances the rate of reaction faster within a 60 and 120 minutes of degradation. And we have also calculated the recycling process for the highest level sample for CIP pollutant. So we can able to see that some minor changes in the degradation percentage has been reduced. So this we can be able to conclude with respect to the materials lost, because once we are using that particular material for the again, so we have to drying process, there will be some loss in the material process. So due to that, we have obtained some variation in the particular degradation percentage in the 3 cycles. And figure B shows about the schematic of the particular formation, where graphitic carbon nitrate, we can able to see that it can able to perform the oxidation reaction where the conduction band is above 0.00.3 minus 0.33 electron volt, and which can able to perform the oxidation process, as well as ZC, zinc cobalt oxide, which is having 1.3 electron volt, which also supports the oxidation process, where two double oxidation process has been happening over here. And this particular is a type 1 heterojunction formation. So in photocatalysts, we've been having Scotchy, type 1, type 2, and type 3. So this particular calculation, this structure comes under type 1. So it is not much noticed in till date. So nowadays we are here, constructions are going on with respect to type 1 and type 3. So most works has been carried out in type 3, type 2 with respect to S scheme and Z scheme. So now we are focusing on type 1 as well as type 3 for the enhancement of the properties of the material for degradation process. So conclusion, we have confirmed about the presence of pure formation of zinc cobalt oxide as well as the composite formation, and we have carried out the morphological analysis through the HSM analysis, and we have calculated the degradation percentage of the particular sample, and we have also confirmed about the scavenger analysis through which the highest radical formation was highest participants of radical is superoxide with respect to scavenger analysis. And these are some of the reference papers which have been carried out for my particular work. Thank you.
Congrats, Roshan, for your nice presentations.
Thank you, sir.
Is there any question? No. Did you check the 20%?
Sorry, sir?
Did you check the efficacy of our 20%?
No, sir, because when we are going for the XRD formation, so we can able to see about the dominance of zinc cobalt oxide. So our main aim is to enhance the property of graphitic carbon nitrate. So when we are going for the composite formation, so we can able to see a similar level of intensity in the peaks. So it may be about the crystalline nature of the sample. So once it is beyond that particular limit, means there may be a domination of zinc cobalt oxide over graphitic carbon nitrate. So where the composition ratio changes and the dominance will be zinc cobalt oxide, these 3 and 4 will be a substitute for it. So our target is to make graphitic carbon nitrate as the main character and zinc cobalt oxide as substituent for enhancing property.
Okay.
Thank you.
Now we have a photo session. Please come out.
Good afternoon to all. Myself AJ Yaswin. Recently, I completed my MSc Masters in Physics at Madurai Kamaraj University. Hello. Good evening to all. Myself AJ Yaswin. In this current academy, I have finished my Master at School of Physics in Madurai Kamaraj University. And my work is on effect of calcination temperature on photocatalytic activity of synthesized lanthanum titanate using wet chemical method. And these are my overviews: perovskite, objective synthesis, characterization, photocatalytic analysis, and conclusion. Perovskite. Let me give a small intro about perovskite. Perovskite are considered as the next generation of solar technology since they are low at cost and very high efficiency. The first perovskite material are found in Ural mountain, which is named after a Russian geologist Lev Perovsky, which has a general formula of ABX3, where A and B are cation and X is an anion. The ideal structure are cubic orthorhombic and tetragonal in system. Significance of perovskite. They are higher active surface. Since they are higher active surface, they can participate in various applications. Thin film solar cell. When perovskite material are integrated into silicon panel, they can produce a lot more efficiency compared to a normal silicon panel. Application in catalyst and conductivity. Application of lanthanum titanate perovskite. They are used in various applications like catalyst, photocatalyst, dielectric material. After doping, it will act as a conductor. These are my objectives: synthesis of lanthanum titanate at various calcination temperature of 600 degree, 700 degree, and 800 degree using wet chemical method. Characterization of lanthanum titanate using XRD. And
Ashwin, go to the result.
In my XRD analysis, we are able to see 3 different calcination temperature, where green represent the calcination temperature of 600 degrees Celsius and red represent the 700 degrees Celsius and blue represent 800 degrees Celsius. At calcination temperature of 600 degrees Celsius, the XRD peaks are observing a poor crystalline structure of lanthanum titanate. When increasing calcination temperature of 700 and 800, the XRD peaks are steadily narrow and sharpen. This may be attributed to the elimination of inorganic constituent during the calcination temperature, which therefore increasing crystallinity of lanthanum titanate. Thus, the data suggests that increasing calcination temperature leads to higher crystallinity. The larger crystalline size, the pure phase transformation in lanthanum titanate. these are my SEM analysis. The three different magnified image of SEM of lanthanum titanate, which is calcinated at 800 degrees Celsius. Here I have particularly took 800 degrees Celsius, since from my previous analysis I am able to conclude that the higher the calcination temperature, the higher the crystallinity. So in A, we are able to see a randomly distributed lanthanum titanate, tiny spear-like particle, and B, we are able to see somewhat bigger like a grain, and C, we are able to see entire lanthanum titanate which is calcinated at 800 degrees Celsius. In a EDAX, the sample are confirmed by energy dispersive X-ray spectrum, and weight percentage of lanthanum titanate crystal are given, where oxygen plays atomic percentage lot comparing to lanthanum and titanium, which in a molar ratio of 1:1:3. And basic principle of photocatalysis: any material that can absorb light and participate in any kind of chemical reaction is called photocatalysis. In photocatalysis, there must be a gap between valence band and conduction band, that is band gap, so it can absorb energy, so it can absorb light and produce photocharges. Working principle of photocatalysis: these are the result of excellent photo degradation of three different samples from the time interval 0 to 75 minutes. I have plotted a graph using origin, and then pure we are able to see pure methylene blue dye solution with no catalyst, and we are able to see there slightly changes. When comparing to 600 degrees Celsius, there are degradation occurs. When comparing 700, 700 has a large degradation compared to 600. While comparing 800 degrees Celsius calcination, lanthanum titanate has a drastic degradation comparing to 600 and 700 degrees Celsius. From that, I have calculated absorption maximum, and these are the C by C naught, which concentration of pure methylene blue dye and concentration of methylene blue dye with catalyst of lanthanum titanate. Photocatalytic activity: the degradation of prepared sample for methylene blue can be seen when there is no light, no catalyst. The concentration of methylene blue did not change. When there is only light but no catalyst, the concentration of methylene blue has slight changes, which can be seen in a naked eye, indicating the properties of methylene blue are more stable. When the amount of catalyst was 10 mg respectively, it could not contact with the methylene blue sufficiently, resulting in unobvious degradation of methylene blue.
Okay, man. Already you told the result. Okay.
And these are my conclusion.
Okay. Thank you. Next, I invite the online presentations. First, I invite Safna.
Good evening to all. Am I visible?
Yes, yes. But your slide is not visible.
Yeah, let me press in this. Is it visible, sir?
Yes, yes, ma. You proceed.
I am Sapna from MES Manani College. I am doing my PhD under the guidance of Dr. P. Charan. Here I would like to present a part of my research work entitled The Influence of Phase Purity and Chemical Compositions in the Broad Frequency Dielectric Responses of VMNO Multiphase Compound Systems. As we know, the transition metal oxides in its pure and dark form exhibit exceptional structural, electronic, and magnetic properties. And many of these properties strongly depend on material defects. Among the transition metal oxides, the oxides of vanadium has widely studied and used in many technologies and hence received distinctive interest in the field of condensed matter physics. Among the oxides of vanadium, vanadium pentoxide
Safna,
is the
Safna,
most stable oxide,
Safna,
and it shows. Yeah.
please go to the result part.
Hello, sir.
Please go to the result and discussion, ma.
Okay, thank you. Synthesized of vanadium manganese oxide for different mole fractions, and this is the obtained X-ray diffractogram of the prepared samples. All the diffraction peaks are indexed as a mixture of both orthorhombic vanadium pentoxide and monoclinic manganese vanadium oxide, without other impurity being detected. The structural parameters are refined using refinement analysis technique, and only a very small percentage of MnV2O6 phases observed. And this is the UV visible spectroscopy of the prepared samples, and the diffuse reflectance spectra of the sample exhibit an absorption onset around 500 nanometer, and transition to higher reflectance occurred around 700 nanometer range. And there is a slight decrease in the reflectance edge with increasing manganese concentration. The small variation may be due to the bandgap restructuring, which alters the conducting behavior of the sample. And I used Kubelka-Munk function to calculate the optical bandgap energy, and this is the Km plot of the samples. And from energy plot analysis, it has been found that a decreasing energy bandgap is observed up to the mole fraction 0.15. And further increasing mole fraction, there is a small increase in the bandgap energy is noticed. An increase of Mn2 plus ions is accompanied with an increase of V4 plus or V5 plus ions. The presence of V4 plus ions narrowing the bandgap, and the presence of V5 plus ions widening the bandgap, because V4 plus has an absorption band centered at 770 nanometer, but for V5 plus it is lower than 570 nanometer. So up to x equal to 0.15, V4 plus increases, and further increasing manganese concentration enhances V5 plus ions, and hence increasing the bandgap. And this is the sum and EDS of the samples, and it shows the highly dense growth of large crystallites with irregular shape and size, with non-uniform distribution of particles in the micron region. And typically, solid-state reaction of metal oxide powders will result in the production of unagglomerated large particles in the micrometer range, and thus leading to highly crystalline solids. Here, the powders obtained showing the same topography. And the presence of elements other than vanadium, manganese, and oxygen are not detected from the EDS spectrum. And the AC conductivity is also studied. The AC conductivity is independent of frequency at lower frequency region and increases with high frequencies. Here, the sigma AC is calculated using Johnshire power law, and according to JPL, frequency independent plateau region is attributed to DC conductivity. And this is possibly due to the short range pairwise hopping between the neighboring particles. So a charge carrier successfully hopped to its neighboring vacant site contributes to DC conductivity at low frequency. As frequency increases, the correlated back and forth hopping causes relaxation of charge carriers and increases the conductivity. And this represents the conductivities of the different mole fractions. And from it is clear that the conductivity, AC conductivity, decreases from 0.24 to 0.103 Siemens per meter. Also, the DC conductivity decreases from 0.186 to 0.074. And the decrease in conductivity is due to the phase component of MnV2O6, which has higher resistivity compared to vanadium pentoxide. And this is the dielectric of the samples. The dielectric constant decreases with increasing frequency for all mole fractions. And this is possibly due to the electron accumulating at the grain boundary, resulting in interfacial polarization at low frequency. But as frequency increases, the polarization, the transition from interfacial polarization to dipolar polarization increases. So the dielectric constant decreases. And when an electric field applied to a material, the electric energy displaces the charge carriers and energy loss transforms into heat energy, which is in the form of dielectric loss factor. So the dielectric loss factor relatively high at low frequencies, which is due to the migration of charge carriers, and migration reduces at high frequencies. Let me conclude my observation. We synthesized V2 minus 6 MnX or 5 minus delta samples through solid state reaction technique, and they are a multi-phase material. And this is confirmed by XRD and ritual refinement analysis. And also the band gap of vanadium pentoxide is tuned into lower energy levels by formulating the complex VMNO compound. The results suggest tuning the band gap of vanadium pentoxide is possible by modeling novel compound systems and varying the mole fraction precisely, and can be used in optoelectronic applications. The surface morphology analyzed using some shown non-uniform distribution of shaped yet large cis grains. The AC conductivity, dielectric constant, and dielectric loss factor of VMNO system was studied in the frequency range of 40 Hz to 10 MHz. The transport mechanism attributed to the small polaron hopping between V4 plus and V5 plus ion seems to be suppressed by the addition of manganese to vanadium and reduced hopping sites in the new matrix, causing a decrease in AC and DC conductivity. So the mixed oxides are lossy material, so it can be used as a microwave absorber. The future aspects, we have to do the XPS to analyze the oxidation states and to fabricate the films by dot plate method, and also to perform the electrochemical analysis and to check the various applications. I would like to acknowledge my sincere thanks to my supervisor, Dr. P. Jairam, who constantly support and guidance. Also, DST for the funding to materialize our laboratory, and IIT Palakkad, St. Thomas College, CMET for different analysis support. So thank you, the organizers of SWAP, for giving me such an opportunity.
Good
Thank you.
presentation, Safna. Safna?
Yes, sir.
Also, I am happy to share that your guide, Dr. P. Jairam, was my student at Adamla University in 2004. Okay, ma.
Yeah,
Okay.
I know.
Next,
Thank you,
I
sir.
invite Alagaraja.
Yes, sir.
Alagaraja.
Yes, sir.
Yes, you start, Alagaraja.
6 minutes. Yes, sir. Yes, sir.
You may take only 6 minutes to complete your presentation. Okay.
One second, sir.
Please put your slide.
Okay, sir. Good evening to one and person here. My research is synthesis and optoelectrochemical properties of bioresource based activated carbon nanoparticles for solar cells applications. Introductions. In recent years, carbonaceous materials have been thoroughly investigated for a variety of applications.
You go to the resultant discussion.
Yes, sir.
You go to straight away. You go
Okay,
to the
sir.
resultant
Sir.
discussion.
Okay, sir. Okay, sir. This is the activated carbon. This one is materials and the methods. Resultant discussions here. From my studies, I can found powder XRD, UV visible spectral analysis, FTIRFS spectral analysis, CD cyclic voltammetry analysis, electrochemical impedance spectral analysis. From XRD, I have from XRD, the activated carbon peak is 002. That means at diffractions at angle 26.3, and the secondary graphite plane is 1001 at 42.4 degree. In additionally activated carbon with cobalt chloride, the cobalt chloride is occurs on 50 at 111 plane and 210 plane at 50 degree, 50.2 degree and 66.4 degree. This proves the existence of dopants in the samples whose influence has rendered the activated carbon more destroyed and amorphous. From the XRD data, crystalline synthesis increases with annealing temperatures. From UV spectra, we have plotted a band gap, that means wavelength with respect to absorbance. From this data, I can calculate the energy band diagrams with energy and E alpha squares. From the UV data, carbon is general on insulating materials with band gap is 5.4 electron volt. The energy band gap observed from the top plots appears to be around 2.7 electron volt for the plain activated carbon. And activated carbon samples with the cobalt chloride is, that means 2.39 electron volt for doping atoms. The band gap reduces even further in the doped case, which shows that the additions of the dopants has increased the conductivity of the samples. From the FTI spectrum, the small less intense peak around 2,928 per centimeters is attributed to the C stretching aligns with the small peak at 2,851 per centimeters. Similarly, 2,111 centimeters per centimeters C triple point stretching. From 1,000 to 622 C double bond stretching, etc. The result supports the conclusions that activated carbon thus obtained so great electrochemical behaviors, and the additions of the dopants improves this activity to some extent. From the CV cyclic voltammeter analysis, from the CV curves, the specific capacitance calculated from the CV curves demonstrated good capacitive behaviors as a result of the activation process. The CV curves for doped samples show a slight difference in shape and the resulting area of curve leading to the slightly better specific capacitance owing to the addition of the dopants. The specific capacitance is particularly relative to the area of CV safe, and evidently the working electrode of doped AC and activated carbon. That means AC means activated carbon has larger CV curve area of the plane activated substance, consistent with the higher specific capacitance. Electrochemical impedance spectral analysis. It may also be due to the interfacial impedance occurring at the interference between the current collector and the active materials. The presence of the semicircle and the straight line, it may be taken to represent a capacitor connected in series with resistors if considered the equivalent circuits. The doped samples shows a smaller semicircle in the high frequency region and an almost 45-degree line flowing in. That means this means 45-degree line flowing. This shows that there is improved electrochemical behaviors as a result of doping the samples. Conclusions. Biomass synthesis have a unique compositions and structure by nature. A sustainable high-capacity carbon can be made using on improved activation process. The activated carbon samples were prepared by thermal activation process with hydrochloric acid to speed up the activations. This method is inexpensive because the precursor is widely accessible and just one step is required for the preparations without need of activating agents. The doped and undoped carbon nanoparticles exhibit good conductivity and efficiency suitable for energy storage applications. They prove to be excellent substitutes and complements for existing technology, which thereby reducing by burden on environmental by providing the clean energy resource. Thank you, sir. This is the future scope.
Okay,
This is the
Raja,
reference.
good presentation. Why didn't
Thank
you
you, sir.
measure the bed surface area of your activated carbon samples?
The surface area.
Because
That means
as
approximately
far as
calculated,
activated
sir.
carbon is concerned, the surface area is very important prerequisite for enhancing the applications.
Okay.
Okay, ma. Next, I invite Menga Sarmava. Menga Sharma? You start.
Okay, good evening everyone. Myself Menka Sharma. This is a scholar from Jamia Millia Islamia. My presentation topic is heterogeneous photophantom catalytic activity of
Menga
cadmium
Sharma, you show your
substituted.
slide.
Okay, these are the outlines of my presentation. Yeah. So I have successfully synthesized cadmium substituted copper ferrite from Soldier rotor combustion method. These are the XRD results. From XRD, I have calculated the crystallite size. As we move from copper ferrite to cadmium ferrite, the crystallite size increases because of the lattice expansion and the morphology of the prepared sample estimated from SEM. There are some agglomeration happening in copper ferrite and as well as cadmium ferrite. The reason of agglomeration may be due to the magnetic nature of the sample. The optical band gap was calculated from UV spectroscopy, and the band gap is decreases as we move from copper ferrite to cadmium ferrite. I have performed the photophantom degradation over two cationic dyes. One is crystal violet and the other one is malachite green. These are the first two, A and B, are the rate kinetics of the crystal violet dyes. From rate kinetics parameter, it is observed that the correlation coefficient is maximum in case of cadmium ferrite, and the degradation efficiency. From degradation efficiency plot, it is observed that cadmium ferrite degraded crystal violet maximum. So as we move from copper ferrite to cadmium ferrite, the degradation efficiency increases because of the correlation coefficient, and on the basis of value of correlation coefficient, all three samples followed first order rate kinetics. That means there is a physisorption phenomena is happening here in between the photocatalyst and the pollutant. The next type, the next pollutant is malachite green. We observe the same result. The degradation efficiency is maximum in case of cadmium ferrite, and all three samples are following first order rate kinetics. So same phenomenon, physisorption is happening here. Because of physisorption, we can say that there is a weak van der Waals force acting in between the photocatalyst and the pollutant. The degradation mechanism for photophantom process, we have used photophantom reagent to degrade our pollutant. So in photophantom, when a ferrite surface is irradiated with visible light, electron and hole pair are generated. So if hole is further react with H2O, it will produce H ion and hydroxyl radicals. And we are using H2O2 as a reagent. So H2O2 reacts with the electron and will produce the hydroxyl radicals that will enhance the photocatalytic degradation efficiency. And Fe plus C ion will further react with H2O2 and will again create hydroxyl radicals. So the hydroxyl radicals are creating by three paths. So that's why the degradation efficiency is enhanced in case of photophantom reagent. We have performed the TRPL measurements to evaluate the recombination time. The recombination time of the time to recombine electron and hole. The recombination time is maximum in case of cadmium ferrite. So this is the reason. That is why the cadmium ferrite performed the best as a photocatalyst. We have performed the scavenger study in which we have used different type of scavengers. One is Ki. Ki is used to, but basically potassium iodide is used to trap holes as a scavengers, and benzoquinone is used to trap superoxide radicals. In case of tertiary butanol, which is used to trap hydroxyl radicals, the degradation efficiency is minimum. So that is why we can say that the hydroxyl radicals is the major active species in the degradation of these two dyes. We perform the reusability test because the sample is magnetic in nature, so we can reuse and recover the sample after the reaction is over. We have performed the reusability test up to 5 cycles, so we can say that the degradation efficiency is there is a less decrement in the degradation efficiency up to 5 cycles. So we can say that the photocatalyst can be reused and recovered after the reaction is over. These are the conclusion. We have successfully synthesized the cadmium substituted copper ferrite from sol-gel autocombustion method, and samples were further characterized by XRD, SEM, and UAVs. The maximum degradation efficiency is observed in case of cadmium ferrite because of the band gap and because of the recombination time, which is maximum in case of cadmium ferrite. Scavenger study has been confirmed. Scavenger study confirms that the superoxide radicals are the main active species in the degradation of dyes. Thank you.
Thank you, Megha Sharma. Is there any question? No.
Okay.
Thank you once again, Megha Sharma.
Should I stop, sir?
Yes, yes.
Okay. Thank you, sir. Right.
Up there. Next, I call upon Jayalakshmi.
Good evening, sir. Sir, can you hear my voice? Hello?
Yes, ma.
Sir, hear my voice?
Yes, you share your slide.
Sir, here, see my slide.
You enhance the slide, ma. Yes.
Sir,
you proceed.
Sir, good evening to everyone. My name is Jayalakshmi. I'm doing research scholar at the Savis College, Kotte, under the guidance of Dr. Anna Vinas. My topic is about the preparation of the electrolyte cream used in the biopolymer for the battery application. Can I move my synthesis process? And this is my preparation of the biopolymer electrolytic cream. For the biopolymer, I take the pectin, and the ionic provider, I take the magnesium chloride. Magnesium chloride. First, I dissolve the pectin in 40 ml distilled water and allow to stir stirrer for the few hours until it attained the homogeneous solution. And then next, I take the magnesium 40% of the magnesium chloride and dissolve into the 30 ml distilled water for half an hour. And then next, I mixed and this two solution into the one beaker, and it allowed to stirrer into the 1 day, depending upon the nature of the film, nature of the polymer, nature of the biopolymers. It's taken hours to dissolve, and then after the final solutions, we have a muddy slurry solution. Then that solution is poured into the petri dish and it is placed it on the oven at the 50 degrees Celsius. And then I have a freestanding. After the drying, we obtain the freestanding thin film, and this is the thin film I obtained, which is shown in the picture. From this slide, we see towards the characterizations of the studies. I first take the XRD and FTR analysis. For XRD, I have take 3 samples. One is pure pectin, and another 2 is 30% of magnesium chloride and pectin, and another is 40% of magnesium chloride and pectin. For pure pectin, we have a peak at the range of 20 degrees, and the next sample we have a peak, but its intensity is slightly low, and the next sample we have a no intensity, and which we have a no intensity, and this reverse there is the complete dissolution of the salt and the polymer, and then next and also it indicates that the increase of the salt concentration, which increase the broadening of the peak and decrease the intensity of the peak. And the next we move to the FTIR analysis. For the FTIR analysis, we have a I have a for pure pectin, have a peak at the 346, and then it slightly move to the 3656, 3293, and this is assigned the OH stretching for the 2, and the next 2136 is moved to peak is moved to the 2142, and 2138 is assigned to the CH bending, and then finally 1368 is moved to the 1202, 1202 in the further 2 peaks, and this assigned as the CO stretching. This movement of this movement of the peak positions is completely revolves the complete interactions between the polymeric chain and the magnesium salt. And the next we move to the thermal analysis. In thermal analysis, first we see about the TGA. In TGA, for the pure pectin, there is a loss at the there is a heat loss at the range of 18%. This is due to the over temperature. And the next two samples, there is a range of the heat loss temperatures at the range of the 25%. This is due to the vaporizations of the moisture in the sample. And then next, there is a loss at the range of 70, 84, and 81. This is due to the breakage of the COC bond. And the next, we move to the DSC analysis. In DSC analysis, in pure peak, that we have a glass transition temperature at the range of 85 degree. And the next sample, we have a transition temperature at 94.1. Which is due to the intermolecular coordination between the oxygen and magnesium cation in the polymeric chain. And the next third sample, we have a low glass transition temperature compared to the previous sample, which is 79.56 degree. And this is due to the weakness of the dipole interaction between the polymer chain, and this reverts the and this indicates the flexibility of the polymer chain and the easy flow of ions through polymer network. And from these studies, it reveals that the PMG2 that sample have a high ionic conductivity than the PMG1 sample. Then we move to the cyclic voltammetry and LSV. In CV, that we have a distinct anodic oxidations at the electrode interface. And the next we move to the LSV, and the LSV is the another important one of these studies, which our electrolyte have electrochemical stability or not. From my sample, I previously said that in DSE, PMG2 has a high ionic conductivity. For that sample, I take the LSV. Then it LSV, and it has been observed that the biopolymer electrolyte of PMG2 is stable at the 3 volt, and it confirmed that the electrolyte is used for the electrochemical application. Then conclusions, for biopolymer electrolytes, I take the magnesium as a ionic provider and the pectin as a biopolymer. For XRE, I confirm the amorphous nature of the biopolymer electrolyte film. And then DSE, DSE analysis reveals the highest ionic conducting sample and the low transition glass transition temperature. For FTA studies, that's a complex interactions between the pectin and MG we shown, and then CV shows the capacity behavior of the membrane with the applied of the different scan rate and voltage. And then next, in LSV the prepared biopolymer electrolyte have a stable of 3 volt. Thank you.
J Lakshmi,
Sir.
your FTR result is not good. Instead of wave number, you put wavelength in the x-axis, and also the y-axis is not correct, which may change the FTR spectrum. Okay.
Okay, sir.
Next, I invite Jay Priyanka.
Good evening, everyone. My presentation is about the citrus peel powder adsorbents for the methylene blue adsorption, and these are the citrus peel powder adsorbents are basically from the agri biomass. Biomass is low toxic, and biomass is why I choose the biomass for my adsorbents is that it has low toxicity and it's highly renewable resources. Therefore, I choose biomass, and among that, why I choose citrus peel powder is that citrus peel powder contains a large number of functional groups. These functional groups are in polar nature. This facilitates the adsorption of dyes easily. And these are the preparation strategies, how I prepared my adsorbents. It is a very simple procedure. Simply, I collected the raw materials and washed and dried it in the oven, and I sieved it in a siever for obtaining a uniform mesh size. That is my raw material. I have shown one of my adsorbents, that is that orange peel is my raw material, and I have dried it in the oven, and I have grinded and sieved. Finally, I received a fine particle sized adsorbents. This is the dye which I taken for my study, that is the methylene blue. The attraction between my dye and the adsorbent is purely based on electrostatic attraction. That is, my adsorbents are basically negatively charged. That is, my adsorbent has a negatively charged particles on its surface, and my dye has a positively charged group. This is known as the chromophoric group in my dye, which is responsible for the blue color of methylene blue. Therefore, the negatively charged particles in the adsorbents gets absorbed with the positively charged part of the dye, that is also known as the azine group. Therefore, the color gets removed. As I mentioned about why I choose these adsorbents is this. These are my UV studies for my degradation studies, and this is the FTIS spectrum. The first peak corresponds to the carboxylic group, and the second peak corresponds to the OH group, and the third peak corresponds to the CO stretching group. That is, the CO bond is present in this is these citrus peel adsorbents are high in cellulose contents. Therefore, the cellulose is responsible for the adsorption and the degradation of dyes. The hydroxyl group is present at the CH position in the cellulose. CH position is more reactive than other OH groups. Therefore, the OH is primary in CH position. Therefore, it facilitates the adsorption of dyes more easily. And the raw lemon peel powder, this in raw lemon peel powder, the semi-major shows are highly unsymmetrical and porous structures. These facilitates the adsorption more easily. Therefore, and in citrus peel powder, there is an highly amorphous phase. Highly amorphous is a characteristic of carbonaceous materials, and therefore, if a material is highly amorphous, the porosity and the porous nature and the adsorption capacity of that material increases. These are the elemental composition. If a material is contains high amount of carbon and oxygen, therefore it increases the adsorption capacity of any materials. And in then I have prepared my adsorbents in two conditions. One is I simply dried and sieved, and in I have sieved grinded particles in, and I have treated it in the N2 atmosphere. Mainly I treated it in N2 atmosphere for its future applications in a fertilizer. Therefore, in N2 treated lemon peel also it shows a highly asymmetrical structure, and in the N2 treated peels it shows a highly amorphous region. As I mentioned above, amorphous is the main characteristic properties, and therefore the lemon peel adsorbents has high adsorption efficiency. And for the same orange peel powder, this first graph is for the raw treated and is for the anhydride in nitrogen temperature. In that raw treated has in both of the adsorbents, the raw treated peel has the highest adsorption efficiency. And in orange peel, the FTR first spectrum corresponds to the COH, and this corresponds to the OH groups, and last one corresponds to the maybe presence of primary alcoholic groups. Raw orange peel has flake structure, therefore it has a small number of pores. Small number of pores means the adsorption efficiency decreases, and it shows a little amount of amorphous structure. Whereas in the N2 treated, it shows a highly amorphous region. Though it has a high amorphous region, but it has a low adsorption efficiency compared to lemon peels. Why? Because as I mentioned above, in some images it has a tiny porous and a small pore size. Therefore, it has a less porous structure. Less porous structure means the adsorption efficiency is not good, is very low. These are the overviews. As bioadsorbents are very cost effective, non-toxic and weekend renewable, and these were used for the removal of dyes and other pollutions. These adsorbents has a large amount of hydroxyl and COH groups. The hydroxyl groups are responsible for the adsorption of dyes, mainly the cationic dyes, and the COOH groups are responsible for the adsorption of heavy metal ions. Therefore, citrus peels are mostly used in the treatment of wastewaters. That's all. Thank you.
They were powder in nature,
Yes,
but if it shows a broad peak, no, where from it originates? The X-ray diffraction. Previous.
This one, sir.
This one, also the previous one.
So it is a carbon and oxygen based material. Therefore,
what is the origin of that broad peak?
That may be due to the presence of oxygen. Yes, sir. Maybe due to the formation of oxides.
Apart from cellulose, which phytochemicals will be responsible for the better degradation of our dye? Because alkaloids and flavonoids are present in the peel powder. Which flavonoid or which alkaloid, which phytochemicals will be more responsible for the degradation of your dye?
Phenolic compounds. Phenolic compounds.
Yes?
Phenolic compounds.
Phenol. What type of phenol compounds? Lot of phenol compounds are there.
So OH and simple phenolic compounds are mostly responsible for the degradation of dyes.
Okay, ma'am. Next, I invite Radhika.
Good evening. My topic is on synthesis and utilization of flower-shaped, downward-shaped copper sulfide for water splitting and other applications. Straight away I go to the experimental technique. Here I have synthesis to the copper sulfide with downward shaped morphology without employing any surfactant and templates, by using only the simplest solvent like ethylene glycol and distilled water. The one of the two ways to increase the electrocatalytic activity of the material is to make it as a composite with carbon like materials, or to increase the electrolyte number of active sites of the catalyst as much as possible. Here I have synthesis to the copper sulfide with unique morphology via solvothermal approach. In XRD analysis, I have obtained the hexagonal phase of copper sulfide. The purest form of copper sulfide is confirmed through the JCPDS card number 780876. I have obtained the through the Sharpix we can confirm the highly crystalline nature of the obtained sample. The through the card we have confirmed the hexagonal phase of the sample, and through morphological analysis I have confirmed the downward shaped morphology. Here this morphology is attained through the viscosity of the solvent. Mainly the viscosity of the solvent have controlled the nucleation of the particles and arranged the material into sheet like subunits and allowed to form like flower like morphology. Through histogram I have confirmed the picture C shows the magnified image. The 2.5 micrometer diameter of particle size have been grown. Through I have employed that electrode material for water splitting purposes for both bifunctional catalyst for hydrogen evolution reaction and oxygen evolution reaction. For hydrogen evolution reaction, I have obtained an over potential of 480 millivolt at 20 milliampere per centimeter square. And for oxygen evolution reaction, I have obtained 391 millivolt at 10 milliampere per centimeter square. We can further improve the performance by adding some composites like carbon materials like carbon nanotubes or carbon fibers. For pure material, I have obtained both low over potentials for oxygen evolution and hydrogen evolution. To calculate the electrochemical active surface area, I have performed the CV in non-Faradic region at different scan rates. Through the CV, we can confirm the double layer capacitance of the material. Through that, we can measure the electrochemical active surface area. I have plotted the delta J values and scan rate and obtained the double layer capacitance value of nearly 3.74 millifarad per centimeter square. This is a good capacitance value for binary for compound. And through electroimpedance spectroscopy, I have measured the charge transfer resistance and series resistance of the material. The series resistance value of 8.75 ohm and charge series resistance of 0.42 ohm and charge transfer resistance of 8.75 ohm have been measured. The low charge transfer resistance is due to the highly enhanced electrocatalytic activity of the material. The electrocatalytic activity has been enhanced due to the electrochemical active surface area of the material. Through this, I have confirmed that the copper sulfide with different morphology have enhanced electrochemical surface area and have good catalytic activity for both HER and OER. I can confirm that it can be accessed as a bifunctional catalyst for the overall water electrolysis process. And main thing, I have synthesized these materials without employing any surfactants or templates. So it is highly possible to construct for industrial processes. and the over potentials can be further reduced by adding some carbon compounds. Thank you.
Yeah, next, I invite you, Mr. Kaliswaram.
Good evening to everyone. I am Kaliswaram from Raja Durachingam Government Arts College, Sivagangai. My work synthesis and characterization of efficient photocatalytic degradation of methylene blue by zinc-doped SNO2 nanoparticles. This is my introductions. The photocatalytic degradations, the 10% molar content degradations, 88% degradation efficiency at the time period of 180 minutes. Then another one pure and 5% molar content, 64% and 74%. In the previous work, comparisons of various publications in this my work. So summary of the work. There is a rootal tetragonal structures were confirmed in the XRD studies. Then the nanoparticles in the crystalline size varied 7.4 nanometer to 10.5 nanometers in the various 0 to 10 molar content in the host materials. And then UV visible absorption spectrometer 349 to 666 nanometer in the absorption wavelength. And then PL analysis 408, 489 and 568 for the pure 5% and 10% molar content. That is a sad patterns as prepared SN2 sample, the diffraction rings as compared to the XRD patterns, the 110 plans at the interplanar spacing.
You got a better result. Okay.
Thanks.
Next, I invite Risa Paul.
A very good evening to all. I am myself Risa Paul, research scholar of Ph.D. Institute of Advanced Studies. Today I will be giving a talk on the development of TiO2 based nanoparticles for efficient degradation, dye degradation of dyes. So, this is the outline of my work. So I'm moving on to the result and discussion. As you all know what is photocatalysis, and it has been famous by Fukushima and Honda experiments. So these are the few applications, and I'm concentrating on the textile dye degradation. So TiO2 can break down water, kill bacteria, and also deodorize all the getting rid of odors, as Fukushima says. So titanium dioxide as a photocatalytic material, these are the features, and these are the three different phases of TiO2. And the main drawback of this is of broadband gap. It is limiting to 3 to 5% of total solar energy, and its photocatalytic efficiency is seriously restricted. So this is the work I am going to present, tantalum-doped TiO2 for efficient degradation of dyes, and this is the photocatalytic reactor that we have been using for degradation of dyes. So we have been synthesized tantalum-doped TiO2 in different constant weight percentage like 3, 6, 9, and we used hydrothermal method for effective, cost-effective method. And this is a structural studies. XRD shows tantalum-doped TiO2 with different weight percentages and also of pure TiO2. In this we can see in TiO2 it is showing pure anodized phase with a small peak of Brookette phase at 211 lattice plane. So we couldn't see any tantalum peaks there. So we have enlarged the predominant peak of 101, and there we can see a shift in TiO2 with the dopant TiO2, a slight shift in the XRD. Thus we come to know that tantalum is present in the TiO2 lattice, and I am showing just FTIR of the main tantalum doped at 3 weight percentage and TiO2 in 987 centimeter inverse. It shows the tantalum bonding with TiO2, which confirms the presence of tantalum in TiO2. These are the morphological studies of tantalum-doped TiO2 with 3 weight percentage. In that, the first are shows of TM images and D of SAD pattern, which confirms the lattice plane of 101 of TiO2 is present in tantalum-doped TiO2. And we have confirmed with IFT patterns 0.351 nanometer of D-spacing, which confirms with the D-spacing of XRD. This is the profile of inverse Fourier transform of D-spacing distance. And these are the EDS analysis of TiO2 and TT3. In this TT3 compound, tantalum is present in very minute percentage, since we have added only 3 weight percentage of tantalum. Then we have moved on for the surface studies, in which we have observed tantalum with 3 weight percentage has been showing the highest surface area of 152 meter square per gram, which shows it is having a good surface area, which will be suitable for photocatalytic applications. These are the optical studies in which DRS measurements have been taken, and this absorbance spectra shows it is absorbing at the range 300 nanometer. And with the help of Kublai-Khammang equation, we have calculated the band gap of TiO2 and different weight percentage of tantalum with TiO2, which shows 3.21 of TiO2, which confirms the experimental results, and then a slight decrease in the band gap. This is the band edge potential we have been calculated with the equation. Then we have got the band edge potential of conduction band edge potential and valence band potential, which confirms the band gap of both the composites. And these are the degradation studies with both rhodamine dye and with both rhodamine dye and methylene blue dye of TT3 sample, which shows in rhodamine dye it shows 97% of degradation, and with methylene blue it is showing 88 to 89% of degradation. And this is the comparison study of both rhodamine and methylene blue with all the composites. In tantalum-doped TiO2, it's showing high efficiency in rhodamine B dye, and methylene blue it's around 80 to 88%. And TT3 is showing 96 to 95% of degradation, and we have done the scavenger test, which shows EDTA and absorbic acid, which shows the material is active species of holes, and then superoxide radicals, then IPA, which is of the hydroxy radical. So my composite nanomaterial shows the presence of holes is in higher. So this is the reusability studies we have done for 3 runs. So it shows a decrement of degradation, since we are using the powder samples. After each run we'll be centrifuging, so some of the sample is getting dispersed, so we could find a slight 9% of degradation decrease. Then we have done for both UV and visible light, and since TiO2 is of UV UV capable of degradation. We just tried with visible how much efficiency it is showing. So further we are planning to do with visible light photocatalyst with this doping like bismuth vanadate, and also trying with MXene. And this is a summary of this work. Tantalum has been synthesized by hydrothermal method and characterized by X-ray, diffraction and transmission electron microscopy and optical studies of Kubel-Kammung and UV visible spectroscopy. Then the degradation of this tantalum TiO2 has been done for both dyes and at 365 nanometer of UV light in 2 hours. Then this tantalum with 3% is showing excellent characteristics when compared to 6 and 9. And also we can conclude that tantalum wastage reduction is also we have been with 3%. And the prepared tantalum TiO2 can be effectively applied as a catalyst for all the trying for degradation process with this experiment, trying for other hydrogen evolution applications also. So thank you. Yes.
And apart from that, what are the other factors contributing for the light degradation? Whether this one is the visible light degradation or
UV and visible. Visible light. Yes, sir. Okay. 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 This is. Yes, this is of UV light and. Okay. This is of xenon light, visible light, and then. Okay. Sir. Thank you.
My next take call upon Abi Belbia. Nice presentation, is.
Good evening, everyone. This is Abi Belvia from Government Arts College for Men, Nandanam. My topic is exploring the potential of rare earth element doped ZNO nanoparticles for dye-sensitized solar cells under the guidance of Dr. S. Sendil. Next, English change. Okay. These are my result and discussion. X-ray diffraction analysis. The figure 1 is undoped ZNO and figure 2 is gadolinium-doped ZNO. So the phases present are 100, 002, 101, 102. These are the phases, and these phases are the major diffraction peaks are 100, 002, 101 corresponded to the phases of 36.5 and 34.2 and 31.1 is the measure degree of correspondent peaks, and the size of the undoped and gadolinium doped ZNO is 20.4 nanometer and 19.21 nanometer. That one is the prominent peaks of undoped and gadolinium-doped ZnO. The next one is UV analysis. So these are my UV analysis results. The first one is undoped ZnO and second one is gadolinium-doped ZnO. So the absorption peaks is band gap of 375 is undoped and 325 is gadolinium-doped ZnO. So the band gap energy is calculated and the tuck plot calculated by 3.18 electrovolt for undoped and gadolinium doped is 3.18 electron volt for undoped and 3.01 electrovolt for gadolinium doped. So next one is HRTM analysis. So clearly shows that a small size spherical type of ZnO nanoparticles provide more surface defects. So the fringes are very clear and it's confirmed that gadolinium and ZnO doped is good agreement with XRD, and the result of interplanar distance were calculated by 0.282 nanometer and 0.279 nanometer for undoped and gadolinium doped ZnO nanoparticles respectively. So the average size of particles is measured by 20 nanometer for undoped and 18.6 nanometer for gadolinium doped ZnO. And next one is EDAX analysis. Usually EDAX analysis spectroscopy is used to analyze which element present in the sample. So it's clearly show pure ZnO is present in the first figure and gadolinium Z and O is present in the second sample. So it's confirmed that my elements are present in the EDAX analysis. So the next one is FTIR analysis. So FTIR analysis, the first one is undoped and second one is gadolinium doped ZnO. So first one was 6.64 centimeter. Inverse is a metal oxygen bonds, and this one is gadolinium doped. 685 centimeter is a metal oxygen, and confirm that yes, ZnO and gadolinium doped present in the metal oxygen bond. And 1650 centimeter inverse and 1625 centimeter inverse is asymmetric stitching vibration of ZnO bonds of metal oxygen groups. So next one is conclusion, and undoped and gadolinium doped ZnO synthesized by one port hydrothermal method, and XRD analysis confirmed hexagonal vertex structure, and the average grain size is 20.4 nanometer and 19.21 nanometer for undoped and gadolinium doped respectively. So the okay, and the HR term is good agreement with XRD results. So I confirm that gadolinium doped ZnO is good photo anode for disensitive solar cells. These are the reference and acknowledgement. I thank my guide Dr. Sendil and Dr. J. Madhavan, Loyola College for the unconditional support. Thank you. Because once we doped increasing in electrical conductivity for dye-sensitive solar cells. Yes, sir. Sir, actually, gadolinium is a light-rate element. It's for a wide band gap. I using that UV analysis. That's why I'm saying.
Sir, here there is a 1 week at 15
Ah, yes, sir.
Correct.
Maybe.
Where?
800 to 600 between. It's ZnO bonds. Metal oxide. Ah, yes, sir. Okay, okay, thanks. Okay, okay.
Next, I invite J. Sakadevan.
Good evening, everybody. My topic is synthesize morphology and the magnetic property of the iron nickel alloy prepared by hydrothermal method. I prepared iron nickel alloy by hydrothermal method. Initially, I have mixed iron nitrate and nickel nitrate in deionized water and stirred for 2 hours. And after that, I have put catalyst NaOH and NH3OH. And after mixing it thoroughly, I have transferred my sample to autoclave, and closed autoclave is kept in hot air oven for 12 hours at the 180 degrees Celsius. Then after natural cooling, I have decanted, filtered, and dried my samples. After this, this is my XRD structural properties of the iron nickel alloys. I have prepared 2 alloys, that is 40-60 ratio and 50-50 ratio. I have confirmed crystalline nature of my both the material by ICST data 10 8456 and 632924. Both confirm the cubic crystal structure, and these are the standard value, and I had calculated this lattice parameter and the cell volume of the material, and it is seen that our material decreases the cell volume. This is the surface morphology of the iron 40 nickel 60 alloy. Here first 2 images are the low resolution, high resolution SEM image. Third one is a DAX image. In that we confirm the iron nickel composition. Slight oxygen is due to surface oxidation. And histogram for iron 4060, his particle size distribution curve confirms average radius of the spherical sphere is 74, and for the case of 50-50 it is nearly 55 nanometer. The magnetic property VSM, the field dependence magnetic property of the both the sample head took, and from that we got cohesive field for the 50-50 is higher, that is 80.21, and for 40-60 it is 70.23. The remnant magnetism for the 50-50 sample is 7.05, and for 40-60 it is 5.70. The magnetic saturation for the 50-50 sample is slightly decreased, seem to be decreased, that is 64.5, and for iron nickel 40-60 it is 64.6. I have a summary. I have successfully prepared iron nickel alloy using hydrothermal approach. We have characterized using XRD, SEM, DAX, and VSM. We got a cubical crystalline structure, and we analyzed. We got agglomerated spherical samples, and magnetism. We got a ferromagnetic property for the magnetism.
Okay. Next, T. Raja.
Good evening to one. Now I am going to present my research work, electrochemical studies of carbon steel in hydrofluoric acid using Coccinia cardifolia plant, leaves as a corrosion additive material under the guidance of Dr. S. Syed Abdahir from Jamal Mohammed College. This is a simple introduction part. This is the aim and scope of the research work. Corrosion additive materials. Reduce the corrosion. Some. In this present study undergoes the corrosion inhibition of carbon steel by using Coccinia cardifolia plant leaves extract to control the corrosion of carbon steel immersed in hydrochloric acid. The following points were concluded based on the above obtained result. The Coccinia cardifolia plant leaves act as a good corrosion inhibitor in controlling the corrosion of carbon steel, is immersed in hydrochloric acid and shows the good corrosion inhibition efficiency. The weight loss technique shows the inhibition efficiency is 96.63%. So the mechanics aspects of corrosion inhibition has been characterized by electrochemical studies such as polarization study and impedance spectra. The surface film has been characterized by FTIR and confirmed the formation of P-2+. The surface film is formed over the carbon steel surface was confirmed by SEM. It shows that the Coccinia cardifolia plant leaves extract has effectiveness in preventing the corrosion of carbon steel in hydrochloric acid solution. Covacais. English name ivy god or scarlet god, sir. Common name is.
Good evening all. Now I'm going to present as my research work as the electrochemical synthesis of MXene using eco-friendly electrolyte. The small quick introduction about the MXene has 2D nanomaterials has a MXene, we can call as a MXene. This MXene is an high electrical conductivity, increased surface area, hydrophilicity, porosity, biocompatibility, introduced by Yuri Gugis in 2011. This material, the MXene was produced from the max phase, which is the max Mn+1 AXN. M is the earlier transition metal. A is the group of 13 and 14 elements. X is the either carbon or nitrogen by selective. This is synthesis of max phase. Then this is the XRD analysis of max phase using various temperature from 1300 to 1500. In 1500, the degradation of the max phase was appeared. So the optimum level for max phase synthesis is 1350. And also we carried out the different mesh size of the graphite. Here the high max phase was appeared as the when changes the mesh size of the graphite size, the 325 mesh size has the appear as the maximum max phase. And then the sintered max phase subjected for electrochemical etching using an as a electrolyte has a oxides and alkaline electrolytes. using anodic oxidation reaction was carried out from 3 to 5 volts. The anodic max phase etched from the electrolyte while applying a potential, and the formation of MXenes used with the terminal groups based on the etchant. This is the X-ray analysis of MXene. While increasing the concentration of the hydroxide, there is formation of the MXene and reduction of the 104 plane, which is indicates of the aluminum, and also the UV visible is indicate that the etching aluminum has the aluminum hydroxide, and also there is a formation of MXene using by analyzing UV visible spectroscopy. Only phase P-2 TI3C2TX MXene was appeared, and also it shows the Tyndall effect with highly dispersed ability due to the formation of MXene with terminal of OH terminal and Cl terminal groups. This is the optimized max phase and MXene. This MXene formation, which indicates that the lower 002 plane was shifted to the lower angle, and also which implies that the layered structure which shifted to the lower angle. This is the FSM analysis of the max phase, and this is FSM analysis of delaminated MXene. This bunch of max phase was after subjected for electrochemical etching. There was a single sheet was appeared. We are the first we synthesized using electrochemical etching method at room temperature. We synthesized as a single layer of MXene material, and this is STEM analysis. The despacing of the each layer is 0.37 nanometers, and also FTR SEM analysis of max phase and MXene. After subjected for electrochemical etching methods, there was indication of OH groups which confirm the vibrational wave number has a 1,650 and 3,005 31 and 3,722, which is indicates that assign of the absorption external water strongly coordinate with the OH2 due to the hydrophilicity of the MXene, which is very important for any material to synthesize has a hydrophilic nature. Then the synthesized MXene were characterized by electrochemical characterization using an why we choose as a positive electrolyte and negative electrolyte here is our synthesized material has a negatively charged, which is terminal with chlorine and hydroxyl group. So we choose as a positive electrolyte and also negative electrolyte. When we subjected for cyclic voltammetric, the negative charge when compared with bar, it was decrease in the catalytic activity due to the negative charge of the our material. It's repelled the catalytic activity of the MXene material. While doing with the ruthenium redox probe, the catalytic activity increases because our material has a negative nature, so it enhances the catalytic activity of the positive electrolyte. Conclusion, mostly the A layer was etched from the parent max phase, usually highly hazardous HF solution, and also the HF is highly hazardous, and also that some of the lithium fluoride HCl etchant were used as etching methods. This is difficult to barrier for scaling up the MXene material. So to overcome this fluoride free solution, electrochemical etching routes were we developed. And for that, we improve the OH terminal groups by using as a etchant as a OH terminal containing electrolyte, which is increasing the D space also, which is facilitate the ion intercalation. So by increasing the interspacing of the MXene, will achieve by introducing any interlayer spacer also, like nanocarbon, polymers and metal oxides, nano and large ions have led to significant improve the composite and potential candidates for electrochemical transducers in the electrochemical sensor. And our studies saw opportunity for the novel material which function as a very efficient for desired properties for various applications like HER, OER and also other electrochemical sensor. Thank you.
Now we wind up the oral session. Okay. Attention please. On tomorrow morning, please present here at 9:30 a.m. Thank you.